Okay. So again, this is our NASA University Leadership Initiative for WINDMAP, Weather Intelligent Navigation Data and Modeling for Aviation Planning. This is our agenda for the presentation. And if you see any changes in what's being shared, just let me know. So we do have a lot to cover today, and we're not going to be able to cover absolutely everything that we've done, but we're going to make sure that we hit the highlights of what we've been working on over the course of the 4+ year effort. So you'll hear from a lot of the task leads on this particular program. We do have a very large and diverse team that we've been working with from multiple universities, including Oklahoma State University, University of Oklahoma, University of Nebraska-Lincoln, University of Kentucky, and Virginia Tech, among other industrial partners, including Vigilant Aerospace Systems and Climavision, and most importantly, our partners at NCAR, National Center for Atmospheric Research, which have been pivotal in making this particular effort successful. So I would like to call out these particular folks. We have had a really great team of investigators on this project. And if you think about all the students that have been involved, each of these investigators, have mentored multiple graduate and undergraduate students over the course of the effort. So very proud of this particular team and everyone that we've been working with on this particular program. And cycling through these, we have had a lot of folks come off and come on as part of it. So going to be highlighting some of the folks that will be presenting here today. So with that, let's give a brief overview of what our problem is and what we're going to be covering. It's really focused on this. When we think about the integration of advanced air mobility systems, including both personal air mobility as well as uncrewed aircraft systems, particularly into urban operations, we have to deal with this particular challenge. How do we fly in all weather environments? So when we're navigating in an urban landscape, how do we deal with things such as visibility, with wind, with precipitation? So this is the real challenge when we think about NASA's mission of integrating UAS and advanced air mobility concepts into a much larger uncrewed traffic management system. Now, this ultimately comes down to being a weather problem. And how do we go through the process of not just observing the weather, but forecasting it such that we can report that data and provide a situational awareness for these vehicles as they're being integrated into the national airspace. So this becomes an in situ data gap problem in the atmospheric or planetary boundary layer. And this has been a known challenge in the atmospheric sciences community that, a lot of our data that is still heavily relied upon for the forecasting ecosystem really comes from, well, let's say antiquated, but minimal implementation for weather balloon systems for radio signs. And while we can fill some of those gaps with both ground systems and satellites, we can't fill the entire gap, particularly when we're focused on in situ data that's critical for things such as measuring thermodynamic and kinematic quantities. So if we look at all of the observations across throughout the US, we can see we have pretty good widespread coverage for these. But when we start to pare these down and we just look at near surface observations, really pulling out the things such as the upper air observations, particularly from AMDAR systems, and then we look at just the atmospheric boundary layer observations, we find that there's a real paucity of data that we're getting. And it's this critical data that's really going into the forecast capabilities. Very important for those folks in NOAA, the National Weather Service, to be able to have this information in the atmospheric boundary layer to do accurate prediction and forecasting, particularly for microscale in urban environments. So this becomes codified in this UAS weather data gap. And when we start to think about the specific impacts that you're going to have for uncrewed aircraft systems, you end up having a lot of concerns at being able to provide this situational awareness for these systems that are operating at lower altitudes, anywhere from the ground level, up to several thousand feet. You start to have this lack of really high quality data that you can use, not just for real-time operations, but in particular for near-term forecasting. So how do you start to fill these gaps that you allow systems to be able to fly in reduced visibility, flying both in, above, around clouds, micro weather systems, particularly for urban operations, dealing with things such as urban canyons, changes in those wind directions, and finally for operations around airports, dealing with things such as wake turbulence and other IFR conditions. So filling the gaps are really what we're focused on. How do we use these systems to be able to do better forecasting? And then provide that for operational safety in particular. Now, when we talk about advanced air mobility, these are the systems that we're really looking at. So both really small scale systems as really large systems too that will be carrying at some point people as the advanced air mobility concepts start to get FAA approval and then start operating in urban areas. So we are looking around this entire range of platforms, both delivery drones as well as passenger drones. Now, what we'll see, our focus is particularly on the former rather than the latter, just due to the fact that as we start to implement these systems, we'll see that there's going to be a greater impact on these smaller vehicles than there are the larger systems, but at the same time, it's a lot less costly to be able to use these systems essentially as our point of departure to be able to ensure that systems are going to be operable within the national airspace. But everything we do is going to have an impact on all scales of advanced air mobility concepts. So there is a lack of validated observations in the relevant urban environments, and that's what we want to really try to improve on. Now, when we look at this from the advanced air mobility needs and benefits use case, so we want to be able to think of these systems that are particularly going to be used for last mile delivery problems. What kind of information do they need to be able to do their job in all weather environments, as opposed to really what they're doing right now, which is just under VFR low wind conditions. So there's a need for enhanced weather information for these systems to be able to operate. Simultaneously, we already know that these systems are particularly useful for being able to operate these weather systems, weather sensors, to be able to improve or enhance our weather observation capabilities. So there are direct benefits in using small UAS to be able to improve what we know and what we're able to see about what's going on in current weather conditions. So these two things are directly tied to one another, and how we design these systems both to provide weather observations or simultaneously be able to provide information from these systems to be able to enhance operations of other advanced air mobility concepts. And like I said, this works across a large scale of advanced air mobility systems, not just small UAS that are used for emergency or for cargo delivery, but also larger passenger carrying systems that are going to be introduced and integrated into the national airspace in the near future. And lastly, all information that we get is going to be directly applicable to improving aviation safety overall, particularly for air traffic control and other on-airport operations. So we start to break this down and go back to that original picture of what we're concerned about and how we're operating these systems, within a boundary layer or micro weather environment. We can really start to pull out the things that we're particularly interested in. How are we doing these measurements in the urban boundary layer? that canopy. What is the impact of things such as both natural and man-made structures on what's happening, how these vehicles operate around these changing wind conditions, as well as some very wind-specific things, turbulence, wake vortices, and shear, things that we're going to see around buildings, around airports, but likewise things that we're going to see that very specific environmental conditions at lower altitude, things such as fog, rain, hail, and in particular icing. Icing is a really great example of this because it's still very specifically dependent upon detailed weather conditions. And so our estimates, for example, in accuracy, being able to predict icing is still wildly inaccurate because it can vary among very small geographic conditions across those fronts, and based upon very small changes in temperature, based upon inversions, the amount of precipitation that you're getting, in across that boundary layer. And that can have a big impact on airport operations. And so if we're able to improve that just a little bit, that's a great cost savings for airport operations directly. So we think about this in terms of our challenges that we have. It's the barriers that the weather produces for aircraft operations, which in particular are going to have a large impact on drones because they're going to have a much larger reliance on the impact of the winds, wind speeds, and wind gusts. And this drives directly into our goal, is to be able to address those needs in real-time weather forecasting. So we want to be able to use that to improve the safety of all low altitude operations, not just across advanced air mobility, but UAS and other manned aircraft operations as well. So the idea behind this then is for WinMap to be able to integrate these real-time observations to fill in this data gap that we mentioned earlier. So our goals for this then is to develop novel in situ observations with drones for assimilation into forecast models. So we'll kind of see that as the observational component. Then develop improvements in urban wind modeling and prediction. So how do we take that data, assimilate it into forecast models, and improve our accuracy of those forecasts, both in terms of time and space, and then finally really implement those from a transition capability into actual operations. So get that information to both uncrewed as well as manned operations to be able to improve overall safety and efficiency of the airspace. Now, we started with several different tasks, and you can see these technical challenges here: autonomous observation, sampling requirements, data assimilation, forecast reporting, and then the unmanned or uncrewed traffic management. And you can really kind of start to segment these into these different components, that those verticals of the observations, the assimilation of modeling, and then finally the implementation components of that. For each of these, we developed what those progress across the time frame is going to be, starting off with technical readiness levels at each one of these and where we think we're at right now. And while we've continuously assessed these throughout the process, we've also tried to be conservative in where we think things are at the end of the overall program. Particularly for autonomous observations, there are now commercial systems that are being developed and implemented to be able to roll these out, to give us a much better idea about how these systems will work. And we have follow-on efforts with NOAA and National Weather Service to be able to integrate these systems directly into their forecasting ecosystem. And that leads us then into a better idea of what some of the spatial and temporal forecasting and observational needs are going to be. The data assimilation piece is still a real challenge, and to be able to take this real-time data and put this directly into the forecasting models. A lot of the models still rely on a lot of assumptions of how this data is being acquired particularly for things such as radiosonde or other balloon profiles. And then be able to really get accurate real-time models out of these systems, have a really high confidence in what those are going to be, and then put that into a forecasting ecosystem to be able to get that forecast in the hands are going to be able to use it in real time. So provide this data directly to the UTM and ATM components that are being used now. Now, if you think about this in terms of our overall strategy, what we want to be able to do is kind of fill this data gap that currently exists. And none of this is to really replace existing capabilities. We're still going to have airborne observations, particularly with AMDAR, with commercial airlines, which again do a really good job of near airport and high altitude observations, in the 30,000 to 40,000 foot range. Radiosondes, which still, really serve as the backbone of that data that's going to the National Weather Service forecasts. That's still going to be there. And of course, ground systems. But these all result in this, sparse sampling challenge that we have to figure out how to deal with. Now, what we want to be able to do is, as these novel autonomous systems, UAS and AM, are coming on board, be able to implement systems on board those to be able to fill those gaps, take that data, assimilate into the models, and then report that back out to this traffic management ecosystem, both on the U side as well as on the traditional A side of the house. So again, we have these kind of three verticals that we're working on. The first of those is the autonomous observations. How are we integrating things to develop this 3D mesonet concept where we have smaller systems that are integrated to be able to provide these accurate measurements? Then at a larger scale, start to use these systems to get better observations for targets of opportunity, things such as severe storms that are going to give us a better idea of things such as tornado genesis, flooding, derechos, and the like. Take this data then and enhance our predictions via observations. A lot of this has been focused on, how do we determine what that requisite sampling needs to be, both in time and in space? How many drones do we need to put within an airspace to be able to provide a significant improvement in that observational and forecasting capability, and then implement this in new fast models. Particularly see results of both of these in the presentation today. And then finally is implementation and integration into the unmanned traffic management system. How do we put this into this DRONEREPS or UREPS concept so we're able to take this information in real time and to be able to provide this so it's actually usable to the end user at the end of the day. And then all this helps make this vision of the NASA airspace of the future possible. So we can be operating systems like this in an urban environment safely and efficiently. So with that, what we'll do is go ahead and start talking about some of these detailed presentations. So our first investigator up is Professor Sean Bailey from University of Kentucky. So Sean, with that, I'll let you take it away.
I think Sean's on mute. Can't hear him.
How about now? Can you hear that?
Yes, I can hear you now.
Okay, my microphone is dead. All right. So can you just go ahead and advance the slide? All right, so our kind of area of operations, we're investigating the surface atmosphere interactions. So it's a pretty broad field. So we approached it from 4 different areas. We did some laboratory studies of turbulent surface or turbulent boundary layer development. And this is kind of more of a long-term fundamental studies, or fundamental set of studies meant to improve our ability to parameterize the surface-atmosphere interaction. We also looked at kind of advancing our ability to do weather observations with UAVs. We looked at different instrumentation implementations, how we can improve that. We conducted field studies in support of the modeling efforts and in support of kind of the data assimilation piece. We did some looking into the uncertainty quantification. So looking at some of the uncertainties associated with UAV measurements. So you can go ahead and flip to the next slide. So the first project, one of the first projects we conducted kind of arose out of the fact that we started this program in COVID and when we were locked out of the lab. So I had graduate students in need of work. So I had to assign them a bunch of old data and ask them to look into different things. So one of the projects that came out of that was a model that was developed by my student Nikolai, which is looking at kind of our ability to predict, to use an eddy population-based model that can predict the turbulence intensity across a boundary layer from basically the surface right up into the boundary layer edge. And this model is adaptable for a wide range of Reynolds numbers. So the current model is only really useful for what neutral boundary layer conditions, but we want to develop it further for non-neutral conditions, convective and stable boundary layers. And then at the kind of the long-term goal would be to be able to implement it is kind of inlet conditions or boundary conditions for LES. So the slide on the image on the right shows one of James's simulations, and you can see that at the inlet of the domain, there's this kind of quiet region where there's not a lot of turbulence. So the idea would be you can take a model such as this one, implemented on the boundaries of these domains, and then you actually have a more natural turbulent inlet state. So that's kind of where we want to go. That's the long-term goal with that one. Next slide, please. And then another study that Nikolai conducted, this is more associated with Jamie's picture of the urban boundary layer or the internal boundary layer that can form within a larger boundary layer. We did a fundamental study looking at kind of the influence of a change in surface roughness. So this is now a change from a smooth wall surface roughness to what's a dynamic roughness. We did a wind tunnel study where we looked at the development of the internal boundary layer across that water pool. And what we were able to develop with that was a scaling approach that would let us scale that internal boundary layer. So that's something that could potentially be involved in surface parameterizations, which would then improve our ability to get better boundary conditions at the edge of at the lower boundary of the domain. Next slide, please. All right, so then that kind of summarizes our laboratory studies, and then out in the field, we were doing a lot of work with improving or developing different ways that we could measure turbulence from UAS. And one of the challenges with using UAS for turbulence measurements is with rotorcraft is that the rotor wash really makes it very difficult to measure the vertical component of velocity. And that vertical component is important for measuring the turbulent flux of mass, momentum, and energy. So what we were looking at was a kind of a way to use multiple sensors, multiple two-dimensional sonic anemometer sensors in this sort of halo array that would then get the sensors out of the rotor wash and let us measure that vertical component. And we had reasonable success with this. Although what we did find was that there were occasions, and on the right, the two panels. The upper panel shows the horizontal component of wind, and the lower right panel is the vertical component. And what we're seeing is we get good measurements of the vertical component on ascent, and we would occasionally get these sort of weird patterns that shouldn't exist on descent. So we wanted to, we recognized that that was due to interactions with the rotor wash. We wanted to get a little bit more of a rigorous understanding of kind of what we needed to do in order to mitigate that effect. So that led us to a series of CFD simulations, and those are on the next slide, where we did a very large parametric study of the flow field around, well, the wind field around different rotorcraft configurations. So we looked at sort of quadcopter configuration you see here. We also have a hexacopter model and an octocopter model. And we looked at different flight configurations, ascent, descent, hover, and different crosswind velocities ranging from 0 to, I think we got hit up to 10 meters per second. So we have this very large data set of these CFD cases. And we then are looking at that now to kind of provide some sort of scaled guidelines that will let people that want to measure wind field with drones know where they might want to place the sensor. So that dotted line that's in the figures on the lower, or on the left, represents kind of a 10% uncertainty. So if you count that as an acceptable bound, then you need to place your sensors outside that range. Good. I think that's the next slide, please. We've also been looking at improving turbulence measurements with UAS, and one of the ways we can do that is by using sort of this old school turbulence measurement technique called hot wire anemometry, which has a very high bandwidth. So we've been kind of playing with getting that onto drones for a while now. And one of the things that we found from accidental study is that these sensors are actually sensitive to droplets in the air. So we conducted one flight with a hot wire probe, and it turned out it was a misty day, and we saw that we were actually able to pick up each droplet as it hit the wire. And looking into that a bit more, it wasn't something that was unknown. Other people have been using this type of sensor for droplet measurements. So we did some wind tunnel work where we put droplets into the flow and measured the response of the hot wire probe, and we're able to kind of get this droplet sizing approach out of the hot wire probe. And we're continuing this work with the hot wires as well. We want to try and get some good inertial subrange measurements and dissipation rate measurements with the probes, and that's kind of something we're hoping to finish up in the last couple months of this project. All right, next slide, please. Good. And then kind of a target of opportunity that popped up. We had a collaborator from NASA Langley who provided us with a infrasonic microphone, a lightweight infrasonic microphone. And what we wanted to do is just, the infrasonic microphone has advantages for potentially long range sensing of storms, potentially low level winds and turbulence. So we wanted to see if kind of putting it on a motorized drone would have any influence on the sensor response. So we did some basically noise subtraction work where we measured the aircraft, or measured the infrasonic response in the lab, and then subtracted that response out from field measurements. We're able to find that we've got very good correlation between the infrasonic response and turbulence that we're measuring in the field. Next slide, please. Okay, so we're now kind of on to more field studies, field work, and then kind of in aid of the autonomous operations piece, we spent some time getting a BVLOS, well, semi-BVLOS waiver for long-range flight over the hills of Appalachia. So this is a fairly rural area. We got approval for that, and we conducted a measurement with one of our aircraft with the goal of seeing if we could measure the influence of surface topography on the turbulence, the low-level turbulence. And what that actually turned out that on that day we measured what are referred to as horizontal convective rolls. So we were kind of surprised to see that, because usually they're not evident over that sort of rough terrain, so we weren't expecting that. But that did provide a great target of opportunity, because we, with these drones, were able to measure very high resolution compared to how these types of rolls are conventionally measured using radar. So we can do the turbulence statistics on those roll structures. And if we then subtract out kind of the influence of the turbulence due to the rolls, we can then, what the slide, the images on the right are showing is that you can actually recover the influence of the terrain on the wind. So the kind of the top right piece is all the wind fluctuations you measured over the course of the flight path, and then you subtract out the rolls, and then you have much more consistent influence of terrain that can be measured. Great. Next piece. Next slide, please. Okay, and then as you'll hear, I'm sure several times later on in this presentation, one of the big kind of capstone pieces was this field study conducted in Tulsa. So we brought a large team down of about 12 people down to Tulsa to support that effort. And we flew 3 of these VTOL fixed wing aircraft and 1 rotorcraft in support of that mission. And we were located at 2 different sites. So all in all, we did one of the kind of the take homes of that is we did 124 flights in Tulsa across all 4 aircraft, and we did this incident-free, kind of helping to demonstrate the feasibility of UAS observations within the urban environment. Next slide, please. Okay, and then last few pieces here. So one of the key components of data assimilation is understanding the uncertainty of the measurements that are going into the simulation or the weather prediction. So we are currently supporting efforts within the intercomparison study that was conducted as part of this Scales field campaign to look at basically the uncertainty that is associated with each and every drone that was flown as part of that effort. That's something that is also still ongoing. And then the next slide. So finally, the last piece that we were interested in was the idea that if you have these 3D mesonettes that are kind of located throughout an area, some of them are going to be more influenced by the surrounding terrain than others. So we wanted to figure out a way to quantify that sort of the uncertainty that's associated with more complex topography. So we did several different flights and throughout the project in different terrain conditions, different atmospheric conditions, and kind of developed a model that can be used to quantify that representativeness error based off of local turbulent conditions. So if you have an understanding of the local turbulence, then you can predict that representativeness error. I think that's it for me and our effort.
Great. Thank you very much, Sean. And with that, we'll transition to Professor Brian Elving to discuss turbulence observations.
Thanks. Yeah, we can go to the next slide. So early in the project, we wrote this paper. This is really Jamie Jacobs' master's student, James Brenner, that we then took his thesis and then did some additional analysis. on, you can go to the next slide. The first part, and we didn't do a lot on this, he had done a bunch of experiments, but and looked at the influence of the rotor on the influence of the velocity field. It identified a region where it'd be best to put a wind sensor, which he concluded that center between the quadcopter and then extended above it. Next slide. This is where we started. Then they flew the drones using that, given that position, and then what we started focusing on is not just the mean, but also the turbulence spectra, comparing between a mast and a small UAS with a sensor in the given position that they concluded from the lab testing. This paper came out in 2022 and showed reasonably good agreement in the turbulence statistics between the fixed mast and the UAV. The issue was there was a lot of uncertainty about the height of the drone relative to the mast because it was just kind of eyeballed. And we also only had a single measurement on the mast, which made it unsure what the local shear was, increasing the uncertainty between the mean and the measurements on the drone. So then we started doing some additional validation testing with this plan of this being the initial part of doing analysis around an urban structure. And so pictured here on the right is some of those initial tests where we've added another small mass measurement towards the ground. So we'd have an estimate of the local shear, and we made a better effort to try to align the UAV at the same height as the mast. You can go to the next slide. Yeah, then following those validation tests, Braden, he really led the effort of taking measurements around this Keir Drummond complex on the campus of Oklahoma State University, pictured in the bottom left there. And then he started making these wind maps, given he had fixed positions where he would hold and record, but on the right there we kind of mapped that out given the around the buildings, and it was hard to interpret these results with only measurements in the space in between those structures. So if you go to the next slide, we did a simple RAN simulation to start to look at expected flow fields given inlet conditions. And not too surprising that we concluded that to really interpret the results, we needed to make measurements upstream of it. So we'd have a proper inlet condition that then we could feed into a model that could be refined given the drone measurements. You can go to the next slide. And then this was our plan. We're going to put a wind cube out in the front, wait for a condition so that we'd set up the same flow pattern as the previous measurements, have the wind cube out in front to get the inlet condition for the modeling. And then we wanted to collect at all these points, give it within less than an hour to minimize temporal variation. And so we were going to have multiple drones flying a various pattern through this configuration. Unfortunately, between the wind conditions, gathering up all the pieces, and then the semester starting and trying to coordinate with that, we haven't been able to run this test yet, but we still would like to be able to have this be the final piece for our contribution. And I think that's the last slide I had.
Great. Thank you very much, Brian. Appreciate that. And next up, we have Professor Craig Woolsey from Virginia Tech.
Thanks, Jamie. You can go to the next slide. So one of the themes that we've been hearing across the presentation and we'll continue to hear is workforce development. There's an awful lot that has gone on and a lot of complementary benefits of a big project like this. And so I'm going to emphasize some of that in my presentation. First, just to start, Our work here at Virginia Tech was primarily focused on that first technical challenge, autonomous observation systems, and we work specifically on wind inference algorithms for small uncrewed aircraft, although the algorithms can apply to air mobility aircraft and larger aircraft as well. So they're transferable in that way. So the outline of my presentation, I'm going to talk briefly about the team. Actually, I'll skip that and talk about them along the way. The research is focused on flight dynamic modeling and identification, model-based wind estimation algorithms. So we develop the model and then we use it to do a better job of estimating wind. And then finally, a lot has gone into validation. And so I won't talk much about publications, but there were something like, a 12.5 journal publications and slightly more conference publications that came out of this. And that gets back to my point about big projects like this and the tremendous workforce development impact they have. We had a team of, I was fortunate to be able to leverage this project to engage 5 PhD students deeply in the work, with another 3 that contributed, something like 12.5 undergraduate researchers and 6 community college students. So we got a great deal of excitement about this big project, and particularly the collaboration with the partner universities. So you see some pictures over there on the right of one of our early gatherings over at Kentucky. Sean Bailey and Suzanne Smith were kind enough to host us out there when they opened their facility. And so that's been a theme throughout the project. So if you could advance to the next slide, please. I'll start with the first PhD student's contribution. And all I've done here is, because I can't possibly convey everything everybody's done, I've stated the title of the dissertation and a big takeaway from it. So James Nutt Gresham, Colonel Gresham, he's now the head of the aerospace department at his alma mater, the Air Force Academy. He wrote a dissertation on aerodynamic modeling in nonlinear regions, including stall spins for fixed-wing unmanned aircraft from experimental flight data. And he's a graduate of the Air Force Test Pilot School and brought a lot of that professionalism to our program here and really helped build up a program that we could lean on. And in particular, his contributions were focused on creating the model that we then use for model-based wind estimation. One of the big contributions was to enable something called remote uncorrelated pilot inputs, in which the pilot maintains control of the aircraft in possibly very challenging flight conditions, but also excites the aircraft in all the degrees of freedom richly enough that we can extract a model from it. And so you go through this sort of iterative process that's outlined in the middle of the slide. This is a well-known flow chart that's adapted from Gene Morelli's textbook on model identification. But the takeaway is that we're able to collect sufficiently rich data in really challenging flight conditions that allow us to create a model that we can then use for model-based estimation. So next slide, please. So the next student, Makonnen Halafam, sort of straddled modeling and identification and algorithm development. And so his focus, I sort of tasked him with looking into the potential utility of including unsteady aerodynamics in these flight dynamic models. So his dissertation, which he defended last year, is identification of unsteady flight dynamic models and model-based wind estimation with flight test validation. And so Makonnen showed how unsteady aerodynamic effects can be incorporated into model-based wind estimation. His approach to wind estimation was pretty conventional. He's using an extended Kalman filter in which the wind velocity is an extended state variable. And so you estimate it along with all the other elements of the aircraft state. And for Makonnen, I mean, his big contribution was a negative result. So I had all this grand idea that incorporating unsteady aerodynamics would basically make the aircraft a better wind sensor. So treating the aircraft as a wind sensor, it's got dynamic response. And so we thought, well, if we can include these more challenging effects, these unsteady effects, perhaps we can get better dynamic response. So to walk you through the pictures at the bottom, that bottom left figure is a fixed wing aircraft, a twin engine fixed wing aircraft with an air data unit sticking out the nose. That air data unit gives us side slip angle, angle of attack, and airspeed. That is there for validation. So that's an independent measurement of the wind at the location of the aircraft. And then we use the onboard instrumentation, the rest of the instrumentation, to estimate the wind from the aircraft motion. And so an example flight outing is shown in the middle, where you see the time history of the aircraft position, and it's following these straight line segments, north and south and east and west. And then that's shown down at the bottom on a polar plot. And so you can see these clusters of points along west, north, east, and south where the airplane's spending quite a bit of time because it's flying straight. And then you see these connecting segments where it's turning and moving to its next segment. And then the wind is shown there in blue. And so on this day with this flight, the aircraft was flying, there was a wind flowing to the southeast. And so we collected data, we developed a flight dynamic model, both with and without unsteady aerodynamic effects. We confirmed, as others have done, that yes, this works. You can do a good job of estimating wind, but in terms of the improvement in dynamic response by including unsteady effects, it was kind of marginal. We get a slightly lower variance on the wind estimates, probably not worth the effort. So okay, well, so that was the big outcome. That's not the only thing McConan did, but that's one of the big takeaways from the work. So if you go to the next slide. So Zakia Ahmed, another PhD student, picked up some ideas that Hub-I there at Oklahoma State has been working on for a while, specifically this notion of using an invariant extended Kalman filter for indirect wind estimation using a small fixed-wing uncrewed air vehicle. Hub-I has applied this to multi-rotor aircraft, and so we thought, well, let's try it with the fixed wing. And the idea is to use symmetry in the dynamic equations to design a filter that works better over a larger portion of the flight envelope. And so like a good PhD student, Zakia started with a good literature review. She and McConan actually worked together on doing a nice literature review of the contributions that have been made and identified some key gaps. And then over at the right, this is the work that Zakia did. So what we see in black in these traces is the true wind as measured by that air data unit. And I've only showed the horizontal components. Vertical components are pretty good. It turns out these fixed wing aircraft work really well at measuring vertical components of wind. Horizontal components are true values are shown in black. The conventional extended Kalman filter is shown in blue dash dot, and the invariant extended Kalman filter is shown in red. And what you see is that the red generally does better, in straight and level flight. It does a bit better, much better in the direction of motion. So this is actually a westerly path. It's that blue rectangle on the plot in the middle. This is a westerly path in that wind to the southeast. And it turns out that those conditions turn out to give you very good wind estimates. The extended Kalman filter drifts. And then that especially is the case in the turning flight segment, which is shown at the bottom. So that's what we're really trying to move toward, is away from this idea that the airplane needs to fly straight and level at constant speed and enable wind estimation in maneuvering flight. And then you could imagine the implications for onboard wind estimation from a maneuvering air mobility vehicle. You don't want to necessarily tell the pilot, oh, can you stop and hover so we can measure the wind? You'd like to be able to pick that up along the way. So that's kind of where we're going with these nonlinear wind estimation schemes. So next slide, please. So Chris Hula Gann, so the people with the nicknames are actually Air Force officers. So I was fortunate to be able to engage a couple of active duty officers who I didn't have to pay, and we had a great project in this collaboration. And so they all contributed to this effort. And Hula's contribution was really on uncertainty quantification and uncertainty reduction. And so his contribution was to use a technique called generalized polynomial chaos to recast uncertain flight dynamics as a deterministic, instead of a random system, a deterministic system where the uncertainty is represented by additional states. And that turns out to be an effective way to computationally efficiently measure moments, uncertain moments, so mean, variance, and so on. So I guess I'll walk through these pictures since I put them on here. The curve at the bottom left, or the curves at the bottom left, are the results of 250,000 simulations, a Monte Carlo simulation with some presumed uncertainties in the aerodynamic model. Remember, we're doing model-based wind estimation, and so uncertainties in the model are going to corrupt the estimates. And so these simulations indicated that the north component was particularly uncertain. And so Chris Gann did some analysis to do the generalized polynomial chaos expansion and showed that first of all, that you recover the mean of those 250,000 simulations straight away. That there's nothing surprising about that. That comes out in the wash. What's more important is that very quickly, you can get the variance and the higher order moments. And so you can really understand the uncertainty very quickly. And then what's even better is that now you have this deterministic representation of this uncertain system. You can now redesign your wind estimator. And in Chris's case, he used something called an H infinity filter, which doesn't require any knowledge of the uncertainty or the statistics of the wind process that you're measuring. And you can design this filter based on this generalized polynomial chaos model and drive the variance down. So you can improve the accuracy of your wind estimates by using this approach to uncertainty quantification. So next slide. And this is the final of the PhD students who were really deeply involved in this effort is Jeremy Hopwood, and he's finishing up this semester. His dissertation is titled Model Identification and Stochastic Nonlinear Observers for Aircraft Maneuvering in Turbulence. So again, this theme of moving from, quasi-steady flight to maneuvering flight. And so Jeremy's introduced a couple of nonlinear observers. One of them is a passivity-based observer, and then more recently he's been looking at something called a symmetry-preserving observer, where he combines these formulations with nonlinear flight dynamic models for both fixed-wing and multi-rotor aircraft. And importantly, these models are accurate over a large envelope. So again, back to James Gresham's work on being able to identify these models. Jeremy has made contributions that allow us actually to identify the models when we don't have an expert pilot like James Nutt Gresham here in the lab. We can actually automate things and safely explore the flight envelope while exciting the dynamics enough to be able to extract models. And so what's shown on the left there are results, validated results of this passivity-based nonlinear observer for maneuvering flight. So that same fixed-wing aircraft, but in a turn. And so what you see there are three different traces. The colored lines are the estimates. The black lines are the truth from the air data unit. What you especially see is that the down component of velocity is very accurately captured. So you get all those little fluctuations just because fixed-wing aircraft are responsive in the vertical direction. That's one of the benefits of using fixed-wing aircraft for measuring the vertical component of wind velocity especially. Then over at the right are some very recent results, and these are simulation results of applying the symmetry-preserving observer. Again, for maneuvering flight, the idea is that we want to be able to capture changing wind and do it from a maneuvering aircraft. And so we have very promising results in simulation that Jeremy is working hard to validate before he finishes up his PhD this semester. So next slide is my last slide, and it's just a quick hats off to Grady Cook for involving us in. We were fortunate to be able to support this NASA Convergent Aeronautic Solutions TTT, Transformative Technology. I can't remember the acronym, but we had Grady led this effort that was a collaboration of a number of NASA sites, and we were fortunate to be engaged in that effort to provide some modeling, some model identification efforts for the aircraft shown on the left and the right in the middle row of pictures there. These were aircraft that were used out at NASA Armstrong Flight Research Center as part of a big campaign to measure wind over the shuttle hangar out there. So on the far left picture, you see that fixed-wing airplane in the foreground, but in the background at the corners of the building, you see a couple of LiDAR cubes that are logging wind data. So it's a massively instrumented area and a long-term data collection effort there. So we provided some model identification effort, and then some, those models then lead into model-based wind estimation of the sort we were talking about earlier. We were also fortunate to be able to host Grady here in Blacksburg at our airfield for some collaborative work that he did with us and with Stefan de Wecker at the University of Virginia to do some dual Doppler making a virtual wind tower with a couple of these wind cubes. I don't have a lot to say about this. I guess I'd have to defer to Grady about that. I will point out Tyler Wilhite, one of the Oklahoma State alumna, works for NASA Langley now, is there in that next to right bottom picture. So lots of great opportunities to collaborate with everyone. I'm excited to be able to share my work, and I guess I'll hand it over to the next person now.
Great. Thank you, Craig. I really appreciate that. Next up is Adam Houston, who's going to be talking about U.S. considerations for atmospheric sensing. Should mention as a starting point, this has been one of the examples, I think, from some of the faculty that have transitioned to other opportunities. And Adam, has, I think, sailed through those storms, admirably being able to, find other great folks to bring on as we first lost Carrie Detweiler and were replaced by Justin Bradley, who's since been replaced by Brittany Duncan on the project. But it's also brought a real diversity of unique ideas to the effort as well. So Adam, I'll turn it over to you.
Yeah, thanks, Jamie. I was hoping I didn't have to follow Craig, but we do. So yeah, it's a pretty diverse group of folks contributing. By the way, Carrick is not dead. He's very alive. He just has transitioned to his focus on his business. He's still a university employee. But yeah, it's been great working with both Justin and Brittany on this project as we've navigated that transition. Some of the early work that we have is was led by AJ. AJ Shankar came in to this project following his participation in CloudMap, which was kind of the starting point for WinMap. I won't talk a lot about this work, but I will say I wanted to include it because it was funded, at least in part, by this project. AJ, working with Carrick, developed a way to transfer cargo using drones, try to solve the problem of short flight times and short cargo transport times. This was published, and I have a list of publications that came out of this the UNL work. But yeah, so he did this both, as far as I understand, both model-based, but also a lot of practical experiments to demonstrate this capability. Next slide. So Daniel should be on the call, and he'll talk a bit about the TAOs. So Daniel, I'll hand it over to you.
Hi, can everyone hear me?
Yep.
Okay, excellent. Yes, thank you, Dr. Houston. So I'm part of the Nebraska Intelligent Mobile Unmanned Systems, or NIMBUS Lab, and as he mentioned, I've been advised by Dr. Carrick Detweiler, Dr. Justin Bradley, and Dr. Brittany Duncan as of late here for this project. And so this all started actually in my master thesis, and it transitioned to my PhD. And the idea was, we first looked at the limitations of current rotorcraft and fixed wings and towers. And we asked ourselves, could we come up with something that is a novel robotics contribution that also can be applied to sampling of the lower atmosphere? So what we came to the conclusion of, well, can we be a deployable tower per se? And then could we stagger sensing elements along the power tether that we're hoisting? So we increase our flight times dramatically. We do lose spatial freedom because now we are physically tethered. So there are no silver bullets. So we introduce a limitation there. But we address the temporal limitation of all other aircraft, and we have increased stability with multiple sensors that are static along the tether. So that's what the picture labeled A here is, and that was published in 2021 to IROS, which is one of our primary robotics conferences. So at the beginning of the project, it was static. All sensors were static. The system was kind of just toss out some tether, hoist it up, and then get some intercomparisons with mesonet towers, as you see there. We have then moved forward and advanced the robotics component on the ground. So the supporting infrastructure to hoist tether beyond 15 meters AGL, because that's effectively surface measurements to most atmospheric scientists. So we want to push it higher. So that means you have to be able to support and manage and optimally control that tether. So we've increased the control surfaces and the mechanisms in the box that'll allow us, in the power electronics, that'll allow a system to be hoisted and maintained at altitude for much longer, and up to 100 meters AGL is what we're targeting. Could you move to the next slide, please? So with that in mind, we also wanted to look at, can we localize the power tether? So this thing is dangling in the air, hoisted, and wind will be a perturbation to this thing. So what can we do with sensor development such that we can now at least derive the positions of the position of the tether and kind of try to back out instantaneous moments of wind direction and speed? So what we decided to do was enhance the sensor suite such that it incorporated inertial measurement units at each of the sensor suites and telecommunication mechanisms. So now we get real-time feedback from all the sensor suites that are physically fixed along the tether. So image D and E are representations of this work that was published in 2023 to the International Symposium of Experimental Robotics. And we were able to calibrate on the fly in order to leverage the theoretical mathematics and physics that must be in place with a catenary that hangs freely, and then use the inertial measurements to actually back out kind of perturbations and positions to varying degrees of accuracy with what we were prototyping. The last thing I'll talk about, and that we're currently working on as we speak, is a paper to IEEE transactions on field robotics. And that's with now, what if the sensors are no longer just these fixed kind of embedded components, but rather what if they themselves were robots, something that we're calling tetherbots. So they're able, that's F and G are showing a couple of these very, very early pre-alpha kind of prototypes, where what if they were mechanized? What if we can now redistribute the sensor suites along this 100 meters of tether in the lower atmosphere to perhaps track various atmospheric information? So we're pretty excited about that direction. And this year, hopefully we'll come to some conclusions on that and publish a journal paper to IEEE TFR. But with that, I think that's all I have.
Okay. Thanks, Daniel. So let me talk a little bit about the work of Stephen Shield, a PhD student who graduated in 23. So his idea was to take advantage of a large data set of thunderstorm initiation points that we had developed over the last few years to, first of all, develop a better understanding of the distribution of thunderstorms over the central U.S., which surprisingly is not particularly well known, particularly the initiation points. But also, and as I'll talk about toward the end here, develop a machine learning model to predict convection initiation. And so I'll go kind of quickly through this, but you can see that some of the things that he did was, number one, establish an optimal method for identifying thunderstorms, which again is something that there are a number of methods, but he actually tested them. The second thing is he developed a climatology using self-organizing maps. So you can see that in the panels kind of in the middle. Some of it's not surprising, the distribution of thunderstorms. We see a concentration over the mountains, a concentration over the Gulf Coast. No surprises there, but with self-organizing maps, you can get a bit more insight. Number one, you can find hot spots and cold spots. That's actually the G-star distribution there in the second panel in the middle. And you can also look at the coefficient of variation to get a sense for how variable these are interannually. And so that's also important to improve our understanding of the variability of thunderstorms. And you see some obvious results and some not so obvious. Well, number one, we get a lot more variability up in the northern plains, where the access to moisture is more uncertain. The access to forcing mechanism is a little more variable. And some less variation where you see persistent redevelopment, particularly the mountains and the Gulf Coast. The other thing you can do with that is better understand the diurnal cycle of thunderstorms, those lower panels. And so this is where the SOCs, the self-organizing SOMs, get a bit more useful. I won't dwell too much on this, but you can actually tease out a bit about the diurnal cycle of thunderstorms. Next slide. And this is where the machine learning model of deep convection initiation comes in. So number one, we can establish how good this model is, but also we can use the model to expose some of the environmental conditions that are most likely to support deep convection initiation, which is an area of active research in my group and other groups. The model itself performed quite well. We also saw that if you train the model over regional areas, you get a bit better performance, but even training it over the entire area, of course, this is just the central United States, the model performs quite well, even when applied to individual regions, including spatial data, spatial information explicitly in the model, improved the model, so the model learns something about the local climatology. And then we can, as I noted, learn a bit more about the environments that support deep convection initiation. So more of a fundamental understanding of DCI. All right, next slide. This is work that is actually led by an undergrad who's now a PhD student at University of Oklahoma, but Ryan Martz was an undergrad working here. He took advantage of this data set that Stephen had developed, the pattern of deep convection initiation, and opened up a door that we definitely walked through with the Scales project, which I'll talk about later, and that is, what is the influence of urban areas on deep convection initiation? So again, we took this database of deep convection initiation points, and he looked at these cities, both small and large, as you can see in the map on the top right. So this isn't all cities across the country. It's just the cities isn't even all cities across central United States, but those that can be isolated from other cities, but also that map out a variety of city sizes from moderate to large. And the takeaway, which it was the main takeaway from the work, is that there is a statistically significant increase in what we call down centroid thunderstorm initiation. And so down centroid is thinking about a wind relative frame of reference just downwind of the center of the city. There's a statistically significant increase in down centroid occurrence of deep convection initiation relative to what we call the peripheral, so on cross stream, and relative to up centroid, so upstream of the city. And we looked at a number of different sensitivities to both the time of day, strength of the winds, and most importantly, urban heat island. And one of the interesting takeaways is that the strength of the urban heat island, or even the presence of the urban heat island, did not significantly change the likelihood of seeing this pattern, which was a bit of a surprise. Okay, next slide. I'll let Grant talk about this one. Grant is a PhD student working with Justin Bradley, so I'll have him take over.
Hello. Like Dr. Houston said, I'm Grant Phillips. I'm also with the Nimbus Lab, same as Daniel, and we have spent some time trying to think how we can expand UAS coverage through distributed drone swarming. So if you think kind of like the Urban Heat Island project, we were using lots of aircraft in a small area. And in a lot of scenarios, more aircraft is better, but then we have to answer questions like, well, how do we safely and autonomously coordinate several UAVs? How do we keep them from running into each other? And that's kind of where some of the questions this work answers. So we're kind of targeting small 450 sized aircraft for this work, testing different algorithms to coordinate them. So we've used a reinforcement learning based approach to get multiple agents and small groups on target and maintaining formations while they're getting there. So that kind of covers how do we position and control these agents. Then we also need to worry about things like real-time collision avoidance and how do we do this efficiently. So we've looked at formal methods and reachability-based approaches for agents to kind of predict where they're going to be in the future, so that if they are disturbed by high winds or malicious acting agents, they can safely avoid other players in the field. And we've also been looking into how can we get the most out of these small agents. They are computationally limited. We're doing lots of things on board. Even just the path planning and collision avoidance takes lots of computational resources. So how can we get these little birds to, or how can we maximize their computational resources? So we've looked into dynamic resource allocation using previous work done by Dr. Bradley. And this kind of this is a very high level overview, but we've done hundreds of flights on the scale of 4 to 8 UAVs. That's kind of generally accepted to be complex enough to say, okay, our stuff is swarming. But lots of flights on a platform similar to what we use for the microscales project.
Thanks, Grant. So this is a follow-on, this component of the work is a follow-on to work that was started back in the CloudMap project, led by Ashraful Islam, who collaboratively we developed a trumpet, we call the trumpet system, for housing the temperature and humidity sensors on multi-rotor aircraft. One of the things we wanted to do is, instead of use this system on a large multicopter, we tried it on the M600, which is, as you may be aware, a pretty large system. We wanted to try on a smaller system that had a bit more versatility. And so just throwing this new trumpet system on a small aircraft, of course, required some experimentation. The intent was to do this experimentation to refine the design of the trumpet and then utilize it in the Scales project and other projects. And so this work was presented at the SR conference in the lead up to the Scales project, which I'll talk about in just a minute. But the idea here is that the configuration of the trumpet was there are a number of parameters that control that. Number one, we have the inlet size, the outlet size, the other things like length of the trumpet itself that we will experiment with later. But just as a quick summary, it turns out that the basic idea here is that air is drawn in by the rotor from the inlet. That's the thing, the trumpet, the bell sticking out on the outside, and then passes through across the sensor, aspirating the sensor, and then exits the outlet, which is right over the rotor. And so to show that the aspiration speed is significant, we needed to actually measure the speed of the flow. Generally speaking, if it's larger than 5 meters per second, we would typically say that that is sufficient aspiration. In all of these experiments, we saw aspiration speeds that are well over 5 meters per second, typically in the 8 to 10 meters per second. But to maximize the speed and to ensure at least the consistency in the speed, we wanted to experiment with sizes of the bells, the shapes of the bells. And the takeaway here is that the outlet size, that is the size that is right above the rotor, is important. Shape was not very important. The inlet size, that's the size of the bell sticking out, not quite as important. Neither was the shape. However, the orientation did matter. So one of the experiments we conducted was whether the trumpet needed to be pointed orthogonal to the flow, into the flow, or opposite that direction. So we found out that pointed orthogonal to the flow maximized the speed of aspiration. All right, next. So as most of you know, there was this project associated with the Flight Week for the ISARA conference. This Flight Week was called Scales and was broken into two components, microscales and mesoscales. And within microscales, there were two subcomponents, the urban heat island component and then the turbulence component. James will talk quite a bit more about the turbulence component. I'll talk a bit about the urban heat island component, which I was the lead of. The whole project was collaboratively led by Elizabeth Smith, James Pinto, myself, Tyler Bell, and Gus Azevedo. But very briefly, the urban heat island component was focused on understanding the three-dimensional distribution of temperature, humidity, in particular, around an urban area. Urban heat islands have been studied for many years, so we weren't intending to expose anything new about urban heat islands, but what we did want to know is how the urban heat island impacted the thermodynamics of the environment, particularly viewed through the lens of thunderstorm initiation. And so the hypothesis is that the CAPE would vary as you move across the urban area. And to do that, then we needed to measure the upstream conditions in the rural. We needed to measure the urban conditions across a variety of land surfaces and the downstream conditions. And so the distribution of points in the map to the right shows the places that we were flying during the Scales UHI portion of the project. Not all of those were flied simultaneously. A lot of the ones that extend kind of radially away from the urban area, we chose based on the wind speed for the day. But in general, we had on the order of 15 flights simultaneously for just the urban heat island component. The UNL contribution to this, we had 5 drones flying. We had 2 sounding systems and 3 mobile mesonets that we were contributing to this project. You can see on the left side of the map all the people that were contributing. There were a number of them. UNL was certainly not the only ones. We had Intermet, OSU, University of Colorado, Meteomatics, the Finnish Meteorological Institute. And so this was a most definitely a collaborative effort. And next, I'm going to have Ben talk a little bit about some of the research that he's doing using these data.
Can everyone hear me?
Yep, we can hear you, Ben.
Okay, thank you. Yeah, hi, my name is Ben. I'm a master's student working under Adam at University of Nebraska-Lincoln, and I'll be using the data we collected in the Scales Field campaign to try and get a better understanding of how the urban environments are changing the thermodynamics in a thunderstorm initiation framework. And Dr. Houston has noted this already, but the work done by Ryan showed that there was a convection initiation hotspot in the down-centroid or downstream of cities. In addition to that, lots of past literature has noted changes in precipitation fields or modifications of ongoing convection as they interact with the city. And I'm trying to get a better understanding of how thermodynamics might play a part in that. In the urban environment, there's going to be changes in temperature. It's going to be warmer, which is the urban heat island, but it's also going to be drier, theoretically. And the trade-off between a warmer and drier environment is going to change throughout the city. And that's why using the scales data is going to be a great way of looking at how the thermodynamic impact changes around the city. But some of the work I've already done so far and presented it at the annual meeting in New Orleans is this work here. If you kind of look at the right side of the screen, that is a time height cross section of the differences between theta E from the urban site and the upstream site. Where you can see the blue values show lower values of theta E in the urban site, and red show warmer values of theta E in the urban site when compared to the upstream. And what we can see is that when we first initially started profiling, that the urban site normally had lower amounts of theta E. But then as time goes on and the sun sets, as we get towards 0Z, that trend might change. Now, we had to stop profiling, and we won't have the data to see how this pattern might have kept going. But it's just an interesting note to see that as the sun sets and the urban heat island really kicks in, we might get some increasing theta E values in urban centers, which could possibly point to enhanced convective potential. And then the graph there in the lower left, that is a graph looking at partial potential energies. And just a couple notes before I explain that, the potential energies were calculated by kind of modifying the full tropospheric soundings we collected with the UAS data, and then calculating the potential energy from the surface to the LCL plus 2 kilometers. And that parameter is based on some previous work that Dr. Houston has done. And what you can see here, this is a comparison plot again, that when you insert the drone data into the full tropospheric sounding, that you get a more of a SIN dominance, or you get more negative potential energy, where you can see those dots there are less than 0. But then that also can change based on if you're looking at a surface-based parcel or a mixed layer parcel. But that being said, there are some notable exceptions where adding in the UAS data increased the potential energy, and we'll still be looking at that to figure out why that is the case. And then last thing is that in the Scales Field Campaign, our drones weren't able to get entirely through the whole PBL. So there's the potential for maybe a few hundred meters above the drone top of urban modified air that we didn't sample, and to still try and get the best use out of our drone data without having to extrapolate anything through the PBL. We'll be using an optimal estimation algorithm, working with the University of Oklahoma to fill that gap. And then for me, I need to just continue work on looking at the different urban sites and finding a way to aggregate that all together and hopefully shed some light on the thermodynamic modifications. Yeah, thank you. That's all I have.
Thanks, Ben. Okay, that's all for UNL.
Great. Thank you, Adam and team. And for those listening in, as you see, we've been moving, from the left to the right on those technical challenges that we showed earlier, gradually going from purely focused on autonomous observations to better understanding of what those sampling requirements need to be. And that takes us to our next presenter, Professor Keith Brewster, who will talk about the observation system simulation experiments. And we're happy to have brought him out of recent retirement to be able to recap all of his work on this effort.
Okay, thanks. Yeah, my retirement is actually a few weeks away yet.
No, that's sorry. I got ahead of myself.
Well, I had a initial plan, I was going to retire at the beginning of March, but now it's more April 4th. So anyway, still, yeah, I will be wrapping this up and giving you some more info on that going forward. Not going to be drying up and blowing away though, so still be around. Anyway, so this is my part of the OU effort as part of the WINDMAP. As others might know, Phil Chilson has moved on, and he had a small group that had started doing some work and is kind of integrated in some of these other things. But as far as my part, and I neglected to put names here, but so this is my effort here, and also we had a student, Vivek Shenoy, who is now graduated and working for the National Weather Service, and Fred Carr is also one of the collaborators. So our work is to answer this research question: can a network of UAS atmospheric profiles, or a 3D mesonet, if you will this improve short-term high-resolution weather forecasts? We've seen some allusion to this concept already, another part of the presentation, but this is our effort here. In this we were using the ARPS model, which is a storm scale model developed here at OU, and we're using this with the IEU and a in situ analysis system, along with WRF, running a nested simulation to provide the so-called nature run. If you're not familiar, the OC is an observing simulation system experiment. So basically you simulate the observations you don't already have and try to see, well, what would the impact be if these simulated observations go in, and you need this nature run to generate your data for that. I'll get to that in a sec. And for this, we have two cases that we looked at. One, Jamie showed some of our very early results on that before we adopted the current data simulation scheme. And then the winter mixed preset case was another one that we've looked at. I'll talk a bit about those next. So this is the diagram of what an OC is. So on the top is a nature run. So we're using a WRF in a nested configuration. And so the idea is to kind of tune this by adjusting parameters and all kinds of things after the fact to give like the very best forecast that actually matches what happened in reality as best you can, and at very high resolution, in this case 1 kilometer. And then we use a scheme to generate the simulated profiles. In this case, we're just assuming a quadcopter type system. I showed a picture in the first slide there of the OU copter song, which is still under development and has come along quite a way during our investigation, but we got some preliminary estimates of errors. So those are important to include as we simulate those observations. And then our work, we also included the Oklahoma Mesonet. This is kind of Oklahoma-centric project. We had the Oklahoma Mesonet, and we also had what we called the FNL, the final analysis, which is something that's produced by NCEP, which incorporates all the other data that we might have in the synoptic scale, like satellite data, aircraft data from commercial aircraft, and of course the weather balloons that are launched twice a day. Those are all in the synoptic data. So we wanted to make sure that we weren't omitting data that might actually be out there in our simulation. And then so then we do the simulation for 6 hours in this case. This is for the spring case illustrated here with the time 12Z to 18Z, and then we had a forecast run out beyond that. So next slide. These are some of the slides where we were looking at convective initiation and the nature run, or this is what we're trying to simulate now, which is very close to the reality on this particular day, which is a severe weather outbreak in central Oklahoma, including some fairly large tornadoes and a lot of hail, mainly. Though there were, tornado was fairly notable. One that went through Moore, Oklahoma. And so you see there in the center of the image, almost just there on the nature run, the kind of big supercell that led to that one tornado. So we want to make sure we capture that. But eventually turned into a squall line running north-south along a dry line, which is the boundary between moist air in eastern Oklahoma and some dry air in the western Oklahoma. And so without the UAV data, the convective initiation along the dry line is much less. It's slower, it's weaker, and I'll get to what's going on there in a minute. And then with having 108 sites, which is over the 120 of the Oklahoma Mesonet sites, and running them up to 2 kilometers, we get a really good result here with the storm just west of Cleveland County there, indicated, I guess it'd be at the coordinate around 450 east-west and 200 north-south, right in that area. I don't have a pointer, I was like, Jamie's running things. But anyway, and we see that come up at this 1930 time and then at 20Z continuing there. So next slide shows one beauty of the OC is that you actually have the truth and you have it everywhere. You don't have to rely on just where the observations are to tell you what the truth is, so to speak. So we can do difference fields, and we just difference, this is mean absolute error calculated over most of the domain. We omit the about 10 or 20 grid points on the frame around the outside, so we're not including some boundary regions, but this is most of the domain. And then we see here no obs is the red dots in all of these. And then we have the different experiments that we ran with just the Mesonet data or that FNL synoptic data or different height levels. FM means the final data, final analysis, synoptic data, plus the Mesonet, and then U at the different levels, either 1, 2, or 3 kilometers. And so you can see in general during the first 6 hours, you see these kind of stair step thing, which shows the data simulation is working. It's bringing in the data and reducing the error down to approximately, or even sometimes below what the assumed error was in these observations. Of course, with multiple observations, you can reduce the error to actually below individual observation error. And then you see as you go out further, of course, error increases. But one takeaway from here is that, the Mesonet does help a little bit, but not too much, especially as you get into these upper levels, 1 and 2 kilometer AGL levels. And the water vapor in particular, you see much better improvement with the 2 and 3 kilometer data coming in over in the lower right panel there. And that lasts all the way out to 12, 14 hours before it starts increasing and approaching what we see with no data. Next slide, you can see what's really going on with that. Like, so especially with the convective initiation, what was going on there was the nature run is on the left there, and this is a vertical cross section east to west, and the dry air is on the left and the moist air is on the right. And you see these pockets of even higher moist air that's get kind of into the blue shades out of the green. And right up next to that boundary is where you get some of the strongest vertical velocities. And in the different simulations, now 400 feet, that's what we're limited to with the FAA right now. You still see a lot of noise out in the dry air there. And the updraft is situated, even though it does create an updraft there because there is convergence along that dry line, but it's in the dry air and it's not really pulling the kind of pockets of higher moisture near the surface in that first 1 to 2 kilometers AGL. And you see that stronger and stronger as you get higher, especially between 400 to 1 and 1 to 2. And not so much of a big difference between 2 to 3. But the other thing that happens is the updraft gets closer and closer to that. So you're actually pulling up that moist air. And in some of these other simulations, you did have vertical velocity, but it wasn't resulting in storms due to the dry air being pulled up. Next slide. Yeah, these are just some of the experiments showing kind of the layout of what we did with the mixed precip case, focusing on just different heights at 25 and 108, and then also at 2 kilometers, like different number of sites. And just for brevity, I'll just show a few of these here. Again, looking at 108 sites. Next slide. For the 108 case. So the truth is on the upper right. So this is a winter case, and this is 1 kilometer reflectivity, or simulated reflectivity actually, but it's similar to the actual observed. And we have like this is winter, so we're seeing snow and mixed rain, and so we wanted to look at kind of a complex winter weather situation here, not just limit ourselves to severe weather. So with no data, some of the labels got dropped here, but with no data on the left, you see there's actually overabundance of precipitation that's created. And then as you move from left to right, this is just with the mesonet data, the second one. And then as you go to the third is with, oh, there we go, 1 kilometer and 2 kilometer. I'm sorry, my frame of my Zoom was covering up those labels. So then you go out 1 and 2 kilometers. And then next, these are similar graphs for a few of the experiments in winter. And the values are a little lower, especially for the moisture, which is the lower panels here. And this is looking at 3 different levels, 10, 1.4, 1370, and about 3 kilometers AGL, different levels of the model surface, and showing the effect on the different variables, and similar to what we saw in the spring case. As you get more data, you get better results. Taller profiles get better results, and that even applies, to some of the lower level fields. You get improved characteristics, say at 1.4, going from 1 to 3 in this case. 1, 2, and 3, or 2 and 3 are similar. And then, of course, at 3 kilometers, you really need to get down to 3 to really knock that error down. But you're still getting pretty good results in the lower right panel at 1 and 2 kilometers. I think overall we decided that like between 1 and 2 is going to be a useful height level for the top of the profile, and 400 is definitely not sufficient. 400 feet. Next, I believe is my last slide. So yeah, this is just showing well, this is the last slide of the impact of the height. And this is the final variable, which is a U wind, and U component of the wind, and similar results. Again, you see the effect of the simulation, and then there's this kind of strong growth in this, especially at the 1.4 AGL level after 12. And I was wondering there, like, well, could we assimilate data later, and would it impact that? So that's the last slide. Focused on this U-wind problem of, how can we stop this error growth? And yeah, so the first one is starting at 6Z, which was what we saw in the last figure. And then at 9Z starting, of course, the data assimilation now goes all the way, it's still for 6 hours, so it's going to go out to 15. But that peak that you see at 18, by including data at 1 kilometer, 2 or 3, you do knock down that error growth between 18 and 21Z. And then, can we knock that down even further? Not so much. As you go to 12Z, you still see the improvement in that window from 18 to 21Z, but the air growth then still goes on beyond that. But if you're looking at the total afternoon, which is when the main precipitation event happened in this domain, that did serve to knock it down and keep at least the air growth and the U wind component. So status of this is we're kind of wrapped up with doing experiments, and I'm in the process of finalizing a paper that we had started a while ago, actually, and Fred Carr had contributed quite a bit to the introduction, which took a little while to get ironed out, and then I'm just adding the winter data experiments, and we'll try to get that published shortly.
All right, thank you very much, Keith. Appreciate that. And with that, we'll move on to James Pinto from NCAR.
Okay, great. Yeah, thanks, Jamie, and thanks for all the speakers so far. So really demonstrating the advancements that we've had to sample the lower atmosphere, and then the most recent talk showing the importance of sampling the lower 2 kilometers of the atmosphere for improving, reducing uncertainties and improving predictability. So I'm going to talk a lot about that in terms of both the importance of having good representation of sort of the mesoscale of the atmosphere, and then how that drives the microscale and the importance of that. I want to point out a number of contributors within our group here at NCAR, including Josh Lave and Jeremy Sauer, who were really instrumental in setting up our microscale simulations that I'll be talking about, as well as Anders Jensen, who is now at NOAA GSL, but he did some of our early data simulation studies to assess the impact of real UAS observations on the predictions of localized wind flows and convective initiation. And then finally, Ryan Sabash did some work with us to look at downscaling mesoscale models to microscale using machine learning. And I'll just briefly touch on that due to lack of time. But yeah, thanks again. And of course, we're collaborating with everyone across the NASA ULI project throughout these research that we've been doing here at NCAR. Next slide. So I said pushing the limits of predictability, and this is a big challenge for supporting urban air mobility, both in terms of providing the weather information needed by small UAS, which are very susceptible to small scale weather variability, including wind gusts and even more localized features that can be created by the urban landscape itself. And that's because of, they're battery powered, they're lightweight, they have slower air speeds. And so they are definitely susceptible to much smaller perturbations in the wind field, for example, than larger transport aircraft. But not only that, but even the systems being designed to transport people across urban landscapes, the air taxis of the future, are also susceptible to these strong areas of turbulence and winds and urban areas that can be set up by the urban landscape itself. And so that's what we'll be looking at here. A key point to make here is that as we go to smaller and smaller scales, they're typically inherently more and more uncertain to predict. So if you hit the down button or advance a little bit. So as we try to get finer and finer scale predictions, the left upside down triangle, you see that the uncertainty increases with the right side up triangle, and especially our small UAS weather requirements are sort of down toward the bottom here. So much finer scales are needed, but these are more uncertain. So what is the hazard tolerance for a particular UAS operation is going to depend on the operation itself and where it's operating. So if you're out in a rural area, you have a bit more tolerance for weather hazards. But if you're in an urban area making deliveries, for example, you're going to want to stick to your flight routes fairly precisely, so you don't go off your route and end up colliding with a building, or even worse, like crashing into a bridge or a moving vehicle on the surface. So one of the things we'll talk a little bit about is how we translate these highly uncertain, this highly uncertain weather information into actionable guidance. That's sort of what I'll get to at the end. Next slide. So here's our vision of the future. Here's an urban air taxi, completely electric and autonomous eventually. Maybe not in our lifetimes, but someday. This is what the vision of what we'd like to see. And so how do we get from where we are now to the future? Well, one thing I'd like to point out is that the 2028 Olympics in Los Angeles are planning on demonstrating this urban air mobility concept with probably not autonomous vehicles, but definitely electric vehicles transporting either players or other passengers from one part of LA to another. And we'd like to be a part of that in providing these microscale guidance predictions that we'll be talking about today. So here's the outline for the talk that I'll be presenting. We're going to start off sort of where we were at the beginning of this project and talk about some of our microscale prediction capabilities that we demonstrated in real time. And then we'll advance forward in terms of our assessment of the impact of UAS weather observations on predicting mesoscale variability, and then transition to looking at microscale predictions in urban areas, and finally a vision of the future. Next slide. So here we are. This was back in 2018, where we were running real-time microscale predictions of weather in a rural environment, but a highly complex terrain. And what I'm showing here is the evolution of the low-level wind field from early morning hours, where we have, hopefully it'll keep running here. See if it's reloading. There we go. Early morning right here, where we have strong flows of wind out of the canyons and into the San Luis Valley of Colorado, which is where the 2018 lapse rate field campaign, the previous ISARA Flight Week campaign that took place. And we were using these simulations to, to determine where we wanted to deploy UAS assets during the campaign, and B, supply information about whether or not there would be hazards. So not only wind hazards, but also hazards in terms of fog and low ceilings and thunderstorms. And so you can see here in the transition, we have the flow coming out of the valley. You can see that there are very sharp gradients in the wind field. And you can see the other thing that to point out here is that this was a very sparse, data-sparse area without the UAS. So there were essentially 3 stars are indicating where the surface observations were. And you can see that they're not very representative of the wind field that was evolving throughout the day. One other thing to note here is you can see the transition of the winds. There's a strong jet here, and then it progresses into a up valley and up canyon flow in the afternoon. So we're going to look at how well our system performed during this time. Next slide. So we produced simulations twice a day. I'm only focusing on the simulations that were generated in the early morning hours. We used a sort of a nested configuration. So domain 2 D02 was a 1 kilometer grid. And then nested within that, we had a LAS domain where we were resolving actual eddies in the atmosphere at 100-meter resolution. So that's the red curves here. And so you can see throughout the week, this is a 7-day period. You see this diurnal cycle of the wind. So in the U and the V component of the wind at that the site at the base of this Sawatch Canyon where we had that strong flow I was pointing out. One of the things you'll note here is the red, which is the LES version of the system, is fairly closely following the parent domain simulation. So this is just demonstrating the importance of getting the mesoscale right, because if you don't get the mesoscale right, you're not going to get the microscale right. And the other thing to point out is that while we were doing pretty well capturing the wind variability in U, so basically the dots are the observations compared to the red and green lines, we were having some trouble capturing the V component, so the north-south component. And so both day and night, we were underestimating the intensity of the northerly and southerly winds. And part of that is because of the lateral boundary conditions. So next slide. one of the first things we realized with this diverse data set that was collected during lapse rate was we have an opportunity to start assessing the impact of UAS observations on weather prediction. And so this was one of the cases we looked at. It was a strong drainage flow focusing on the northern part of the San Luis Valley. Strong winds emanating from the canyon to the northwest into the San Luis Valley. And you can see where the assets were deployed on that day. The blue symbols are from the University of Kentucky. The red symbols are from the University of Oklahoma. And then we also had the CU Data Hawk in the brown there. The other systems that were being flown, we left out so we can do some independent evaluation, including the NSSL mobile mesonet and radiosonde data, and the University of Nebraska mesonet, mobile mesonet as well, which is that hard to see with that black line located there. In this example, we're comparing predictions obtained with and without data assimilation of UAS observations to a LiDAR located at that white star. And so the white star itself shows the typical pattern that we saw every day, where we have strong northwesterly flow emanating from the canyon during the early morning hours, and then transitioning to an up canyon flow between 14 and 15 UTC, which is about between 8 and 9 a.m. local time. The middle panel shows the result if we didn't do any assimilation. And you can see that in this case, the northwesterly flow, while it weakens as the daytime heating takes place, it does not reverse to an up canyon flow. And just also note here, the top of the Doppler wind LiDAR that we had located at that white star is roughly about 200 meters, but we show sort of above that just to show how the model is evolving the rest of the atmosphere. The bottom panel shows the result after assimilating UAS observations, and a couple of key features jump out at you. First of all, we're now able to simulate the transition from northwesterly flow to southeasterly flow and actually capture the timing very well. But also we capture this sort of descent of the higher momentum air toward the surface right before the transition of the flow from northwesterly to southeasterly. So these two features are well captured after we assimilate the UAS data, and are of critical importance if you're trying to do planning, obviously, for UAS flights. You really want to know the timing of and the magnitude of when this wind shift is going to happen. And this paper and these data experiments have been published in Jensen et al. Next slide. So now we're looking at a time series of data. So similar to the comparison with the Doppler wind LiDAR, but here we're just comparing with the surface station at Saguache, also right near that white star. The magenta dots are the ASOS observations for this day. And what I've got highlighted here is the period of drainage winds shifting to up canyon or up valley winds. The black curves are without data assimilation, and the blue curves are adding in data assimilation. And so you see right away again that without the assimilating the UAS observations, we really cannot capture the evolution of the winds from northwesterly flow to southeasterly flow. And this is actually a critical piece of information for creating microscale predictions in terms of the turbulence and turbulent eddies that form in this flow. The other thing to point out too, in the right here, the temperature predictions weren't too bad, but they were adjusted slightly more positively as well with the comparison between the black and blue. But you see in the moisture field was greatly improved with the assimilation of the UAS observations. So this kind of feeds into some of the work that Adam was and Ben were showing, the importance of capturing the moisture variability and improving this simulation of moisture in these environments. Next slide. So with these early studies, we were demonstrating the potential value of UAS observations on mesoscale weather predictions. That also, during this time as well, I was working with the WMO to organize a global UAS demonstration campaign, which was being planned for 2024 and which actually has happened. We'll talk a little bit more about that here in a minute. And on the right here is an example of using UAS observations to improve the prediction of convection initiation. And this again was another case study from the lapse rate field campaign that took place in the San Luis Valley of Colorado. And so in the middle panel, you'll see the difference between no assimilation versus, or sorry, in this case, we were assimilating the surface observations. There were a few of those in the San Luis Valley for the control run, which is the blue curves. And then comparing that with the simulations when we add in the UAS observations in terms of assimilating them as well. The gray curves are the actual observations that weren't assimilated. So these are from radiosonde data. So they were our independent truth. And we can see again the moisture, even here as the dew point, is much more better related to the observations after we assimilate UAS observations. And this impacts the CAPE and the LCL to some extent as well, which turns out to be critical for simulating convective initiation. So that's what's shown here on the right. So the top panel is the radar reflectivity. You can see that a strong storm had formed by this time just to the north of one of our profiling sites. The middle panel shows the comparison of the simulation with simulating only the surface observations with the stage 4 precipitation data. So that's those purple sort of magenta type colors there. And again, so they correspond pretty well with the radar reflectivity as they should. You see there's intense area of accumulated precipitation just to the north of the OU profiling site. And then after we assimilate UAS observations, we see we have a much better depiction, maybe a bit overdone, but it's important to capture these initiation events because again, they're going to have a big impact on UAM and UAS operations, and we really need to have a handle of when and where these are going to occur. So this was another example of a positive outcome of assimilating UAS observations. Next slide. So now let's advance forward to 2024. So as I mentioned, the WMO UAS demonstration campaign took place in 2024. It actually started in March of 2024 and continued through September. And the Scales campaign, which was already mentioned a couple of times by Sean and Adam Houston earlier, took place at the end of this WMO demonstration campaign. And it really actually leveraged a lot of the infrastructure that the WMO campaign set up, two of which were establishing a data standard for UAS data files being collected, and also setting up a dissemination framework so that these data could be uploaded to the cloud in real time and then disseminated around the world to modeling centers for them to ingest into their modeling systems. So this is a big advancement between where we were before in 2018 when data formats weren't standard. There was no way to get data up into the cloud and potentially used by users around the world. So huge advancement there. And so the Scales campaign, as Adam mentioned, had two different components. There was a mesoscale component and a microscale component. The mesoscale component was really set up to demonstrate the 3D mesonet concept, which was alluded to earlier by Keith Brewster and I believe also by Adam to some extent. And Adam also mentioned that we were sort of the scientific steering committee along with Tyler Bell, Gus Acevedo, and Elizabeth Smith. So we were instrumental in sort of organizing this and bringing together essentially the largest ever simultaneous deployment of weather UAS in the world. So this is a huge accomplishment. And the 3D mesonet concept included up to 13 or even more profiles flown simultaneously at those circled dots, the circled symbols and the map on the lower left there. You can see we're covering a domain of about 200 by 200 kilometers. We even had participation sort of indirectly by a private commercial company called Zipline, who were providing their data while they were doing other services. These are known as symbiotic observations. So they're making package deliveries, but they're also collecting observations and providing them as part of the data set. And then on the right there, you can see this distribution of profiles that were collected throughout the week. And this is just one example. We had these going up and down at either a 30-minute or an hourly strobe. So we have really good spatial resolution as well as temporal resolution. And then nested within that, we have this microscale, even denser network of observations that we're using both to evaluate the urban heat island effects that Adam talked about, and also looking at the turbulent impacts of the urban landscape on the lower atmosphere. Next slide. Now, if you click on the image on the left there, you'll see this is an example of the University of Kentucky vertical takeoff and landing vehicle that was collecting turbulence measurements during scales. They were flying 3 systems, pretty much with continuous coverage throughout the day. So once one would land, another one would go up, and collecting key measurements about the turbulence in the lower atmosphere. Several other platforms you can see it's going counterclockwise. All of these platforms are able to capture high rate information, so we can see what the impact of the urban canopy was on the turbulence in the atmosphere. Next slide. Here you can see our site locations on the left, and these are overlaid on our microscale model called Fast Eddy's domain. The full domain is shown in the outer box, and then this red inner box is indicating the sort of the downtown area where we zoom in on the right. And then you can see where the UAS profiling sites and turbulence sites were located for microscales. We had one to the south, essentially due south of the urban landscape, at a place called Riverside West Park. And then another site located just to the southeast, which we used a little bit toward the end of the experiment. And then we had several sites to the north, and these were all flown by the University of, well, 2 of them were flown by the University of Kentucky, and then a third site was flown by the University of Virginia to characterize really fine scale variability near a single building. On the right there, you see the depiction of the urban landscape that we see within Fast Eddy. So this is what Fast Eddy sees when it's doing its microscale simulations. The BOK Tower there in the center is the tallest building in Tulsa at 205 meters. And then you can see in the zoomed in portion here, you can see where we had the University of Kentucky flights, as well as I forgot to mention the OSU Doppler wind lidar was positioned pretty close to the the University of Kentucky multi-rotor copter that was flying next to it. So Josh Lave set up these experiments and ran them. And we actually had him run an experiment almost immediately after the campaign, once we picked one of the days that we thought would be most interesting. And we'll talk a little bit more about that next. So if you click on this one, this was a simulation of the microscale environment around Tulsa on the 10th of September from scales. On the left, we have the wind speed, and on the right, we have the resolved turbulence from Fast Eddy. One thing you'll note right away is in the left, you can see the wake forms downstream of Tulsa. So you have lighter winds and a pocket of air, and you can see how as the wind direction shifts, that pocket of lighter winds rotates around, as you would imagine, as the wake basically follows the streamline flows of the air. You also see some areas of enhanced flow. So those brighter colors are areas where the winds are getting channeled around buildings. So this is at 35 meters above ground level. And those channeled areas where you have the stronger winds correspond really well with the areas of enhanced turbulent kinetic energy. So these are areas where we're expecting aircraft to run into more intense pockets of turbulence, vortices shedding off buildings, and so forth. And the interesting thing about these turbulence wakes is that they can persist several kilometers downstream. So, for example, the turbulence stream that forms off buildings in the southeastern corner of the domain, as they're starting from here, you'll see they start to propagate downstream and persist for several kilometers downstream. We also looked at the depth of the perturbations and turbulence. And so this is just showing how the turbulence intensity generated by these buildings propagates upward and downstream. And so In the morning hours, you can see that there's fairly strong and turbulence up to about 300 meters above ground level, so 900 feet. In the afternoon, it's about the same top of this turbulence layer, but a little bit more diffuse. And this is predominantly caused by the BOK tower, but other large buildings in that area as well. You can see in the right panel where the two cross sections were made. Next slide. So one of the things we wanted to do is see if we could actually sense the variability in turbulence with the UAS platforms. And so this was data generated by Sean Bailey after the experiment, comparing the green dots, which were observations from the UAS that they flew, the vertical takeoff and landing UAS that I showed earlier, compared with the fast eddy turbulence at 3 different levels. So at 53, 105, and 206 meters above ground level. So the ranges, the heights above ground level match up with the heights that were flown. And so a couple of things you can see right away is that the evolution of turbulence throughout the day is fairly well simulated compared to the UAS observations that we had during that time. So if you're doing 13 and 16 UTC, we see a ramp up of the turbulence. And then we see a bit of a lull, and then another peak that I have circled there in red, which is very interesting because it corresponds at 17 UTC with one of these streamers of turbulence that passed over the UAS site where they were flying. So this could have been coincidental, but it's interesting that the same level of variability that the model's producing is actually being observed by the UAS in the field. So very interesting. You can also see the depth of these layers, fairly coherent. So this purple shading, you're having turbulence values of over 1, which are quite intense, really. You'd probably be bumped around a bit if you were flying one of these UAS in that area. They're very coherent as well. So they span the full depth of the lower 200 meters of the atmosphere. Next slide. One of the key things to point out here, if you toggle that back and forth there, is if you, go back to that. So the two images on the left, it's basically showing you the impact of having a 30-degree error in your boundary conditions. So you can kind of see how the wind field and the areas where the wake and the enhanced flows set up is quite a bit different with just a 30-degree offset in the lateral boundary condition wind forcing. So on the right there, we essentially quantify that to show, if you go down one more, there you go. So you can see the difference between the red and the blue arrows. So the red is the shift into a more of a southerly orientation of the winds. And then you can see the magnitude, the brown area is indicating where the winds are up to 6 meters per second slower. And the blue area is indicating where the winds are up to 6 meters per second stronger, just due to a small shift in the boundary condition winds. So this really points to the importance of doing a good job of constraining the boundary conditions. And the only way you can do this is with more detailed measurements that weather UAS can provide. Next slide. So here's the overall concept. Yeah, and you can start that animation too, Jamie. So I showed this figure on the upper left. We really need to have a dense network of observations. Sort of the 3D mesonet concept is going to be really important to fill in the data gaps where we don't have observations, to better constrain the numerical weather prediction models. We've set up a framework where this data can be downloaded immediately and uploaded to the web so that modeling centers around the world can ingest them and ultimately assimilate them. The bottom panel there is showing the evolution of, in this example, winds. But so not only do we have this denser network, but in certain situations, we also want to have very fine temporal resolution to assess how the atmosphere is changing in dynamic situations where you might have severe convection that might form that day. So you can sort of figure out, use this targeted approach where you realize you really need this higher rate data as well. These data feed into numerical weather prediction and data simulation systems to produce ensembles to help characterize the uncertainty. And then we can use some way to pick an ensemble member, for example, maybe a representative ensemble member to drive these microscale predictions. If you click on the movie one more time, this is actually data from the Tulsa field campaign where we ran Fast Eddy. We coarsened the data a bit just to be able to animate this reasonably. But on top of that, we're flying, this is the Black Swift S1 fixed wing aircraft, and it's flying a pattern. And we can kind of compare the measurements from the Black Swift vehicle to Fast Eddy, which also should be updating underneath. There it goes. We actually have much finer resolution Fast Eddy data, both in time and space. And so we need to update that for this plot, but this is just a concept of what we can do. Providing guidance to UAS so they know, hey, we're running into an area that's going to have intense turbulence. And the UAS itself is saying, yeah, we're seeing this intense turbulence. We need to adjust out of here. The bottom right there is showing another method where we can use machine learning and artificial intelligence to downscale ensemble predictions at the mesoscale to try to predict where the fine scale turbulence is going to exceed some threshold. So this is just an example of a probabilistic product that we created of the TKE. The yellow color is indicating where there's more likelihood of intense turbulence. So again, uncertainty information is going to be important, and figuring out what the thresholds are for safe and efficient operations is going to be important, and especially in urban areas. And then my last slide, again, just kind of looking at the vision for the future. We have what we'd like to do is be able to provide these high resolution and microscale predictions to the data users so that they can make better decisions in the field, and also provide these data to modelers so they can make improved forecasts. And on the right there, we see sort of a mock-up of what could be done in terms of providing users, UAS operators, information about what to expect along their planned flight route. So in this example, we're showing sort of this out and back trajectory on the left. And then as part of that trajectory, we get this information about, okay, we're going to have a headwind going out, and then coming back, we're going to have a tailwind. And then while we're flying, we can maybe adjust the forecast, or at least know how accurate it is by looking at what the data was actually being sensed along that flight route. And then finally, on the bottom panel, translating this information into actionable guidance in terms of your likelihood of mission success and whether or not your battery is going to have enough power to get you from point A to point B and complete your mission. And yeah, we'll take questions at the end, I guess, and wait until.
Well, we did get one question, so we can go ahead and try to answer this in real time, James.
Oh, okay, sure.
So there was a question on the domain that you were using for data assimilation during lapse rate.
In terms of the size of the domain, or where?
Great question.
Yeah, it was basically, I mean, where we were getting the observations were in the, throughout the San Luis Valley. So this is actually a picture right here of the San Luis Valley again. Most of the observations were in the northern part, and our domain extended well out beyond these mountainous areas that you're showing here. Sun-graded Crisco Mountains on the right and the San Juan Mountains on the left of that image. One of the things I didn't mention, but we did notice that the impact of the observations was about 5 to 7 hours, I would say. And in these examples, which are a little bit less than some of the impacts that Keith was showing in his OSSI studies. But we definitely had a smaller network of observations during lapse rate. It'll be interesting to look at the data from scales, because we had a much larger, more dense network of observations.
Great, thanks, James.
Yep.
Okay, with that, and again, I apologize, I haven't been monitoring questions during each of the talks, but that's the only one we've had so far. So let's move on to the next vertical, which is our implementation. And Nicoletta Falla will be giving this presentation, and she's again another one of our faculty who started off working on the ULI effort here at OSU, and she has since transitioned to professorship at Auburn. Nicoletta?
Thanks, Jamie. Okay, so for implementation, we're going to change direction a little bit. We're not going to have the cool pictures James had, but we looked at how systems and algorithms we're developing can help the community as it exists right now, but also in the future. So how can we help stakeholders that we expect to find at low altitudes in the airspace, and how can we use them? So, we envision that all these algorithms, all the systems we're developing will one day either enhance or replace weather sensing capabilities right now. So if we replace all balloons with UAS, we have more freedom to move around, but we also have more challenges. So that's all we looked at. So our initial work here focused on better understanding of how the community uses weather information right now in different locations and what they would need in the future. Again, with the understanding that they don't really know what the future could look like. And then we transition to how to best integrate all these weather sensing UAS into the current airspace without creating adverse impact. Next slide, Jamie. So I'm going to keep it pretty brief here, but we did publish all components of this work. You can go and look at the papers that are available online, publicly available. We do have one more paper coming out for Nicholas's work on the last question there on modeling the impact that will hopefully be out before the end of the summer. Next slide, Jamie. Okay, so going back to the beginning, understanding how our operators use weather right now, we went at this from two directions. One was quantitatively through a nationwide survey. We asked pilots and GA pilots at the low altitude and also US operators a series of questions. And we also asked them to identify what their preferences are and how they're using all this information. So I'll show you three of them. One of the questions was, how frequently do each of these weather elements influence your decision to fly or to cancel your flight? Not their flight itself, but how are they using this for decision making? And we had some difference between UAS operators and GA pilots, which was to be expected. But essentially, we're trying to use this information to make sure that anything we come up with should not be used by one community on its own, but rather should be used for everybody. Essentially, the way current weather products were designed for pilots, and they're not as useful to UAS operators as they could have been. We're trying to fix it so that in the future they're useful to both, given that they have different requirements. Next slide, Jamie. The next question we asked them was, how satisfied are you with current weather products? I knew for myself I wasn't very satisfied with winds aloft data, and it seems like most GA pilots don't share my views on that. But we had some differences between UAS operators who seem to need more dense data on winds aloft and convective weather, as opposed to GA pilots. They have less of a need for that. Okay, next slide, Jamie. And then another question I want to point at was, how frequently do these weather elements cause you to cancel a flight? And we're looking at type 2 errors here, where let's say you had a campaign scheduled for at 6 a.m. in the morning, the night before the forecast said it's going to be bad weather. You cancel it, you wake up the next morning, and you realize you had canceled it for nothing. So this points towards efficiency, where we are not being unsafe, but we are wasting research time or flight time. And it seems like for GA pilots, clouds were more often wrong than UAS operators, which kind of makes sense. We were talking to current UAS operators who are at a low altitude still, so clouds are not likely to get low enough to where they will impact them without them knowing. On the other side, surface winds were impacting UAS operators more than GA pilots and so forth. And next slide. So once we finished with this, surveys online, we had about, I want to say 660 participants who gave us feedback on how they use weather products. We went on to a more qualitative approach with focus groups to get more context on what's actually happening. And we had conversation. We tried to create focus groups where we had both US operators and GA pilots, so they could talk to each other and essentially contrast each other so we could see how they're using things differently and how things impact them differently. And we asked them questions on how they plan a flight, how they plan a campaign, what they look at, what their process is, what weather systems and what weather products they use, how often they check for the weather, how far ahead they start, and things like that. And then we also asked them for any changes they would like to see for their particular use cases that would help them be safer and more efficient. And we won't go through this in too much detail. One of the theses published, so this work resulted in 2 master's theses and 1 PhD in work. So one of them did a thematic analysis where they identified what was mentioned more often and how it should lead to changes. And Jamie, if you want to switch to the next slide. But one of the examples here that kind of surprised me and my student, because we are not flying UAS very often, right? So one of the things that surprised us is that we would expect that we would need more weather at higher altitude or at mountainous terrain where things can get unsafe pretty quickly. But on the UAS side, one of the things mentioned was that in flat terrain like Kansas, it's actually harder to guesstimate what clouds are doing visually because it's all flat, as opposed to in the mountains, they know the peaks of the mountain ranges, so they can compare the cloud coverage to those and figure out how high the clouds are. So that was a pretty new thing for us, not having flown UAS much, that kind of helps us identify things that we maybe kind of counterintuitive. Okay, Jamie, next slide. So switching from all of that, we said, okay, well, it seems like they want more weather sensors at some locations or different altitudes. So we tried to figure out how the addition of these weather sensing UAS will impact other traffic in the airspace. Because anytime we add something, of course, we'll have an impact. And for this, we used an agent-based model that we developed, where we had 2 kinds of agents. One is aircraft that are currently in the airspace, and the other agent is a weather sensing UAS. With the weather sensing UAS, we're able to change the trajectory and decide what altitude to go to and things like that, or how sparse they are in the airspace and all of that. With the aircraft side, we just took the airspace as it exists. We developed statistical models to essentially model different areas and different times during the day, as well as different seasons. And we created an environment where they could all coexist. Next slide, Jamie. So we identified 2 kinds of events, loss of separation events, and we can see them in that weird looking sphere there. So we've got the sphere in the center, the white sphere, where that's loss of separation 1, where we're just following RSVM limits for vertical separation and ICAO limits for horizontal separation. And anything that falls in that is a loss of separation event. We also defined a second event where where you can lose horizontal or vertical separation, but while the other direction is below a certain threshold. And we made sure that all of this is changeable. So we were designing the framework more than the results. So then anybody can take this model and adapt it to their own sensing, to their own UAV, essentially. It doesn't have to be weather sensing, to see how it's likely to impact the airspace. And we also evaluated our framework on 3 different areas for different operations. So we took Reno, Nevada as an example of a terminal maneuvering area where we have dense traffic, but we also still need the weather sensing UAS to be present. So we also took North Central Oklahoma as a representative for a rural area that has a high amount of general aviation traffic and also military traffic, but perhaps not so much commercial traffic at the low altitude, no airlines. And then we took the entire state of Indiana because it included a lot of flyover traffic, but also it had big airports like Fort Wayne, Indianapolis, and Cincinnati, where we have bigger airplanes flying at lower airspeed and lower altitudes when they're taking off and landing or on the approach. And I'll show you on the next slide, Jamie, some of the things we've been using it for. So essentially, we have this environment we're initializing by pulling representative traffic from that particular area to build a representative day or an hour of traffic. We also initialize the UAS we have at the frequency we want them. We can predetermine their trajectories. So I think for most of these, we chose spiral up trajectories. So essentially start at the surface and keep spiraling up at a constant radius to get to essentially replace a weather balloon. We can also change that to where we are flying a larger range, but at the same altitude and things like that. And we check for initial conflicts we want to deconflict initially. Then we propagate all of the agents with respect to time, and we see if there's any conflict coming up. So then we counted the different kinds of occurrences to figure out what the impact was. Next slide. So this is one of the examples we used it for. This is the case where we did the entire state of Indiana. And you can see on the left, we've got a more sparse distribution of weather sensing UAVs. The blue dots are the weather sensing UAS. And on the right, we've got a more dense case. We'll just, double the frequency, right? And you can see on the graph, so we have a frequency of of conflicts per UAS. And depending on how sparse the area is, we've got, so for example, in the early afternoon, we've got most occurrences. So where at least each UAS was causing about almost 2 occurrences. So that's something we would rather avoid. Perhaps in the afternoon, we'd go with a sparser approach, and then during in the night, we go with a denser grid or things like that. So other variables here are, again, we can change the trajectories. It doesn't have to be a grid. We chose a grid because it was easy to represent and figure out what areas we would avoid. For example, in Reno, we identified that obviously the UAS that were closer to initial approach fixes for approaches were more impactful. In Indiana, we don't show it on this figure, but the Louisville area as well as the Evansville areas are more impacted, which was kind of surprising that Indianapolis in the center there was not as impacted. But again, that's because we've got traffic landing at the position where the UAS was operating. And I think that's my last slide, Jamie.
Great. Thank you very much. Appreciate that. Thank you, Professor Falla. Next, we'll transition to Professor Azevedo. And I think as a precursor prior to Gus getting started, you should mention that our initial plan for holding annual conference events and field campaigns was derailed somewhat by COVID. And so we used that as an opportunity to hold biannual events instead. The first of those being in 2022 with the Weather Technology Forum in Tulsa, and the second of those being in 2024. And so our field campaigns became much more targeted, but at the same time, I think those allowed us to scale up those campaigns to much larger events. So Gus, I'll let you take it away.
Thank you, Jamie. And also, before I start talking about the ISAR flight campaign, I want to make an additional comment to the NASA team and extend an actual thank you to the NASA team and to the community here, because as Craig and many have mentioned before, a big part of this is the development of the workforce. And I am one of these examples. As I started with WinMap during COVID as a graduate student, in the middle of my graduate studies, lost my advisor and funding, and through the community here represented here and WinMap funding, I was able to finish my doctoral research and transition to research faculty position with OSU and continue working on WinMap and continue developing the next generation of students that are to come. And this presentation here also goes over all, I think, the steps that we've seen so far with the development of new technologies for sampling the environment and integrating that into forecasts and then into operations, which again, the thank you extended here to the community that I was able to, in my doctoral research through WinMap, do the system that is focused on winter mixed phase precipitation, which was also a very unique system that I'm not going to focus on this presentation, but it did represent potentially the first multi-model data fusion of UAS-based, both remote and in situ sampling with the integration of a phased array radar on the UAS. And so to Jamie's point, right, with Matt twice, part of it was the Weather Technology Forum in 2022, but here I want to focus a little bit in 2024, which was our latest meeting that had two components. First component was the conference week and then the flight week, which had all the targeted observations that Sean, James, and Adam had mentioned before here. So for the conference week, we had 100 plus attendees with 47 presentation and posters with academia members from both the US and international institutions. We had friends and partners from government agencies and industry participate. We had an excellent student integration throughout the event where students were able to not only present their work, but be part of technical discussions and consult with the experts from different institutions. We also had a really interesting integration with the Tulsa Aeronautical and AAM ecosystem, extending the opportunities that are available in Oklahoma through the broader community so that we can advance the research and make this next generation of aviation a reality. And we had, as a part of this event, a very interesting discussion that you see the picture on the right there, on the bottom right, about the future of this airspace management and the integration of AAM into the national airspace. Next, please. And so under that spirit and with all that you've seen here presented so far, the flight week that followed the conference was designed not only for incredible scientific achievement with the SCALES campaign, but also as a proof of concept of several ideas that will be important for the NASA going forward. First is that idea of scales itself, right? How these mesoscale, phenomena that we're used to seeing in the current observation infrastructure, how they roll in through and roll through the state, and how they produce different weather patterns. But most importantly, how these mesoscale features produce microscale features once they encounter the transitions from rural to suburban to urban environments. And we were able, through simultaneous measurement, get a very unique data set that will allow us to explore both, right? Because we had, as Adam and James both presented here, we had those rings of measurements where all these people were flying at the same time. And so we can study both isolated microscale ideas, mesoscale ideas, but also I think this was a very unique experiment because it allows us to attempt to initially see if there's any correlation between the two. Next slide, please. Thank you. Also, as part of this study, because all these different systems, which were 36 different systems from different institutions from the US and abroad, would be distributed across the state, we had to create a baseline between their measurements so that once they were in different places, we could correlate them and understand if the difference that we were seeing between a measurement in one point and another point was in fact due to a change in atmospheric condition and not just a simple bias or effect of that particular system. And so this intercomparison study was done on the very first day of the flight week. And it was very interesting because not only gave us a unique opportunity to understand the differences between these systems and create this baseline, but also it marked a few very interesting firsts, I think, in our community. And as James mentioned, all of this data collection was done with the support of the WMO Weather UAS demonstration, but also in support of the WMO UAS demonstration. And so if we could go to the next one. A first interesting point of this intercomparison study was that for the first time, I think in our community, we not only had UAS payloads that were designed for vehicles be used as reference instruments outside of UAS vehicles, and you see there the OSU tower that had a fast response UAS equivalent payload without the potential biases created by rotors, et cetera, as a point of reference. But also it marked the first time that we had a reference UAS flying with all other UASs to give a comparison point, not one comparison point, pardon me, actually several comparison points throughout the profiling range, right? Which usually we struggle because the area in which we need operational comparison, right? When all of the system is presenting all its characteristics is exactly the area in which we don't have measurements. So it becomes a chicken and the egg situation where how do you validate this new tool if you don't have any tools in the same environment to validate against, right? And so through multiple ground-based instruments, radiosondes, the reference UAS, and some interesting post-processing techniques that Tyler Bell, Sean Bailey, and I are working together on. We're creating this very unique data set. And so the idea here was that the UAS would, the two test UAS would ascend with the reference UAS and come back down and hover near the ground reference system so that we could create both the link to the ground-based systems, but also understand how that link could be extended upwards. In addition, as was mentioned by James here, this was a very unique opportunity to link back to the lapse rate effort that happened in 2018, which also had an intercomparison study that was led by Lindsay Barbieri, and created at its time a very unique data set of how all these systems performed, right? And so we made a point to make our data set backwards compatible to that data set, and that's also a portion of the hover, which is how most of the data intercomparison was done during lapse rate, so that we could create a secondary snapshot that allowed us to look at the first snapshot and see trends and the evolution of these systems in this 6-year period, and see if that provides any insight as to how we're going to go forward. And we are already seeing a couple of things, as Adam presented in his portion of the presentation here, how some systems have been improved. His Trump system was improved and miniaturized, and how he was able to multiply that same system in different units and create bigger geographical distributions. If we can go to the next one, please. And so here are some examples of the systems that we use. We use the traditional Oklahoma Mesonet towers because they have a unparalleled historical track record of good measurements. In addition, a lot of the systems that were used as a reference, both the tower UAS payload reference system, but also the reference UAS have been developed inside their calibration laboratory infrastructure. And so we have a way to go back to the original calibration references to these systems. And then later during the deployment, that gave us a way to cross-validate what was happening near the deployment sites if they happened to be near another Mesonet station. And then you see the example on the top right of the reference UAS, and then on the bottom right of a new commercial system that is entering our community being compared to the reference tower instruments. Next one, please. And so finally, as I mentioned, I was able to transition within this community, which is a unique privilege. But also in my new role, I'm able to help new students coming in and train the next generation of workforce. And so here's some student and activities that are related to WinMap that we've been working on. The first one is being done by the OSU master student that is doing the initial looks of the lapse rate data set, particularly from a perspective of aircraft and system design and how that relates to what is going on now in 2024. We have a couple of undergraduate students looking at a new system instead of being done like Daniel has presented here for data collection, but actually to calibrate and understand the aircraft design impact on the system. So it's a tethered system that also moves, but it's on a balloon because we want to eliminate the issues caused by the UAS, the potential issues caused by the UAS with rotors and aircraft boundary layer, and understand how we can design these systems better. And we also have some additional efforts in the standardization and both on the standardization of the measurement, but also in the standardization of how the measurements are disseminated. And finally, just to mention that Dr. Avery and Dr. Jacob and I had the privilege of also teaching a short course at the last American Meteorological Society meeting to create also broader awareness of this new technology so that the next generation of meteorologists know that this is a technology that is maturing and it's going to be a resource that's available for them to use in their research and operations, actually. I think that is all for me.
Great, thank you, Gus. I appreciate it. Our final vertical is really focused on the transition to commercialization or operations. How do we get this technology in the hands of the companies that will be able to utilize it in the field? So we initially had two companies that we started working with. First is Vigilant Aerospace Systems, which is really focused on detect and avoid capabilities. How do you manage flight trajectories in conflicted airspace operations? And the interest there is integrating the weather data into that operation. And the other was AeroS, which is really focused around the operational capabilities. After the first year, AeroS ceased operations, and so we started looking for another partner. At that time, we deemed it that we were mature enough on the operational side that we really wanted to focus on, what we could really push for weather operations. And that's when were able to coordinate with the Porva Bahaj from Climavision. And so, Porva, I will turn this over to you to discuss about Climavision's role in the project.
Hi, good afternoon, everyone. Thank you, Dr. Jacob, and thank you for inviting the Climavision team to join WinMap. Just from a stage setting perspective, you know, we are a commercial provider of weather technology, weather observation technology, and modeling services. So it's been a privilege, you know, and a pleasure for us to join this team to track what's happening in this space. As someone in the commercial side, you know, we're always looking for different opportunities. We've been focused a lot on the energy side of things and working with public safety and emergency management, transportation in general. So participating in all of these WinMap meetings has really helped us to start narrowing down our offerings in the UAS and AM space. So today's presentation, my name is Apoorva, and I manage our public sector weather radar programs, and I'm going to talk mostly about that and how that's been informed by the work here. And I also have on the call Dr. Young Hui, who is a senior atmospheric scientist from our team as well. And we'll both be available for questions later. So the first part that I wanted to talk about was the weather radar infrastructure itself. And that's basically this ability, you know, what you're seeing on the map over here with these circles are basically radars that have either already been deployed by us or are in the process of being deployed in various states where WinMap operates. And the goal is to get better observations closer to the ground. All of these circles show a range of 60 miles or about 4,000 feet. So we really focused on getting observations close to the ground in order to support UAS and AM operations. Next slide, please. So what I've got over here, as we've rolled out this network across the country of supplemental weather radars, I've got a few examples to show that hone in on some advantages that we see that this type of radar technology brings to not only to UAS and AM operations, but also to general aviation. One of the key areas where we found a lot of value from these systems is when we're looking at snowstorms, you know, and snow events that result in reduced visibility for pilots. So I've got a few cases to discuss about that, to show you that. So this was a case back in October with the radar that we've installed in Kentucky, shown by the blue circle. This was a case where basically, you know, if you look at all the ASOS stations that were nearby, they were not reporting any snow on the ground. But if you go to the next slide, when we looked at what the neighboring weather service radars were showing, and you can see examples of 3 radars on the right-hand side, because they're all measuring aloft much higher than where a lot of these operations take place. You know, an average user would look at those types of observations and say, well, it's snowing, so we should not be flying. Whereas if you look at the image on the left-hand side where we had a radar installed locally on the ground over there, we basically saw nothing because, you know, a lot of these snow observations are close to the ground. A lot of the snow is taking place close to the ground. And this was a good example of a use case where it helps to have this additional validation with a local radar because you're not unnecessarily canceling a flight that you could have otherwise made. Next slide. The converse is also true where in instances where you have examples of events like lake effect snow, where there's a lot of precipitation closer to the ground, if you don't have a nearby weather service radar looking at that space, you're going to completely miss the storm. So this is an example where we have a radar installed in the Erie area in Northwest Pennsylvania, and you had a lake effect snow late last year. If you go to the next slide, It's actually pretty, you can see this was a pretty impactful event with a lot of snow accumulated very close to the coast that day, resulting in whiteout conditions, blocking down traffic on I-90. And if you go to the next slide, hopefully the video works. Yeah, you can just click on that. You can see the comparison between what the left-hand side is showing is basically what the Buffalo radar from the Weather Service was observing with this snow event, and then the right-hand side is showing what we were observing. So you can see a lot more intense snow that we were picking up. I don't know if you can click that and if that animation plays.
Yeah, unfortunately, it's not working.
Oh, no worries. So basically what you would have seen is like, this whole green blob of, showing lake effect snow moving continuously over a couple of hours over the region. Whereas on the left-hand side, that if you were relying just on the Weather Service radar, you wouldn't have seen that. Going to the next slide then, it's why we found these particular radars that we're deploying to be really helpful with snow measurements. The other place where we've seen it impact general aviation as well, and this is a good example. This is a radar that we installed and are operating in Missouri. And in this case, there's a very clear outflow boundary that was ahead of the storm that was picked up very nicely by our radar and our reflectivity and velocity images. And you could see it track all the way towards the next rad radar that didn't pick it up till this was right next to the next rad radar. And again, this type of event, it validated against an ASOS measurement on the ground of high wind speed. This is the type of information that could take down the type of wind event that could take down a GA pilot or UAS or AM operation because it's completely invisible on radar. Next slide. So this is really the last slide, just to give you a sense of how we're going about this problem. All of these orange circles here show our existing weather radar network in the country with the Weather Service NextRad system. The blue circles basically identify locations that we plan to install radars to improve our situational awareness close to the ground. And over the course of the WindMap project, we've installed 29 radars across the country, shown by the green circles, that are all now operational and available to the Weather Service for their operations. And then, we work with different state-level DOTs and with different researchers, many of whom we've got introduced through this particular program to, start planning field campaigns where they can match up our data against other measurements. So that was the last slide, but I did want to also talk about, the other whole piece of our learning for, coming out of WindMap has been, the importance of all of the numerical weather modeling work. And so from the commercial side, so we've been looking at, what we can do at this end. So we do run our own global model at 8 kilometers, similar to the GFS. We have our own supercomputer. On top of that model, we run like a 2-kilometer resolution grid, similar to the HER, which is at 3 kilometers all over the US. And then we have some nested domains running at 0.67 kilometers. All of this is informed with, the data assimilation that Dr. Youngwee and his team do, where we bring in not just radar data, but other sources of data as well. We're hopeful that at some point we can start bringing in the UAS observations as well into our data assimilation techniques. So I just wanted to keep that short and simple and pass that back over to you, Jamie, and we're available for questions.
Great, thank you, Apurva. I appreciate that. So unfortunately, Crately Epperson could not make it today, so I'm just going to highlight some of the work that they've been doing. Okay, they've been, our commercial transition partner since the beginning of the project. And really what the focus here is using their software that they've been developing, which was really started as a fairly immature piece of software at the beginning of the project, which is based around the NASA Stratways algorithm. So they have an exclusive patent with NASA, utilizing this particular algorithm that they can integrate and then commercialize. The real focus here is to be able to take what we're providing as an input into Flight Horizon to be able to expand the capabilities and provide better flight safety situational awareness with operational weather hazard data, both in real time. So being able to take that information that's coming off systems that are operating in real time, and then be able to integrate that with the forecasting and eventually nowcasting system to be able to have that tracked directly into the Flight Horizon software. So they've been working with an in-car piece of software, a system called Titan, which is thunderstorm identification, tracking, and analysis and nowcasting, to be able to provide that information directly into Flight Horizon capabilities. So since this project started, where they've been able to get is something that essentially looks like this. And if you're a UAS or a AAM operator, you can either have this on your ground station or in your cockpit to be able to see what these storm tracks are going to look like that provide you a level of additional hazard awareness, both in real time and in the future. And this is a good example of this. What you see here is this, your aircraft, operating here, your own ship, as it's, traversing along its trajectory, will start to intersect with different areas of both current and future severe weather. And this could be anything from visibility to hail to high winds, depending upon what your different thresholds are set at, so that you can track this. So as you're moving forward in the future, what you'll do is use this NASA Stratways-based algorithm, which is initially developed to avoid conflicts with other aircraft, where now you're essentially using this to avoid conflicts with other potential weather hazards. In this case, a severe storm. So as your aircraft is moving, it provides that information about what that system should be doing, and which you can either utilize to provide informational decision-making capability for the pilot, or be able to use that directly in an autonomous capability. So the next phase of this is really taking this to a full-time, real-time weather and airspace visualization capability. So you'll have this completely integrated for your AAM operations that provides you a map of what your safe hockey pucks are going to look like based upon other aircraft in the area. But now you've integrated this with real-time weather information with a forecasting capability on top of that. So you can track that information directly. So that really ends our set of presentations that we have today. I'm going to provide just a real quick summary, just to wrap things up, about where we've at and some of the things I'd like to highlight. Again, we haven't been able to show you everything that we've done over the course of the project, but all that will be provided in the final report and some of the stuff that has been presented at past annual meetings as well. I think, one of the things that we're particularly really proud of is our culminating flight campaign. This was always part of the effort to be able to pull these components together from the different teams and weave that into a really profound demonstration of what the capabilities are, while simultaneously pushing the science forward. I think we really did do that across the entire team, those represented in WINMAP, as well as a lot of partners that were not directly involved in WINMAP, but benefited from this particular exercise. And that allowed us to leverage in both directions to be able to expand what the reach of WINMAP was, but at the same time, they were able to use WINMAP to leverage their own science and aviation weather goals as well. We'll say from experience, from the lapse rate campaign that we conducted in 2018, that the data analysis from this is going to go on for quite some time, certainly through a good portion of 2025, and beyond. So, we'll see lots of stuff come out of this particular campaign in the near future. Yeah, as James Pinto had mentioned, this was really this was the largest gathering of weather UAS ever. And as far as we know, it's kind of the largest collaborative experiment of its kind as well. And this just gives you an example. If you think about all of these sites, each of these sites had pilot and commands, had visual observers, had students that were involved. So it was not just a great scientific experiment, it was a great workforce development opportunity to really give these students a one-of-a-kind unique experience in not just operating the vehicles, but acquiring the data and then going through the data analysis process. This is now being leveraged, as we're seeing in the current federal climate with issues with losses of position and funding. How can the National Weather Service, for example, start to implement some of these ideas and concepts of the 3D MESNet into their actual operational environment? That's ongoing now with the Tulsa National Weather Service site, essentially leveraging the results of this experiment to determine what is the art of the possible to be able to make these systems work, to be able to previously supplement weather balloon flights, but in some cases, as we see that some sites are canceling their weather balloon or radiosonde launches due to lack of staff or funding, that these may actually replace some of those at some point in the near future. But for that to happen, a lot of what we've talked about still has to be finalized and implemented before we make that a reality. One of those is getting the airspace approval to be able to fly these systems up to much higher altitudes, which is currently ongoing within the Tulsa site. And then taking those systems and operating them in a way that can eventually be autonomous, so that way you don't have to have the pilots monitoring the systems as they're going through the process of flying these vehicles and getting the data, and then making that data assimilation component completely automated as well. Data is being automatically transferred in real time, and the National Weather Service then being able to take that in and implement that into their forecasting models. So with that, I would like to end here. I know we've gone a little bit over time of what we promised, but we would be happy to distribute and take any questions if there are any.
Well, Jamie, I have several questions, more like discussions. But let me first check in with Kaushik and Meena for programmatic aspects. So they might need to slide into another meeting. But for example, Kaushik, Meena, Jamie has a link to guidance on the final report. Is that the way?
Yeah, I believe I sent you the guidance on what needs to be included in the final report. I just wanted to say this was an excellent presentation, a good overall summary of the accomplishments by the team, and allowing all these students to get some real time experiences, and was wonderful. So thank you very much.
Thank you, Meena. I appreciate those comments.
Well, Jamie, I since this might be the last time we're all together, I sort of wanted to have maybe a quick discussion along the lines of what's next. And along those lines, I have some questions here, maybe to pose to the group. First though, if Nicolette is still on, let me welcome her to the state of Alabama. I recently moved to Alabama myself, so I didn't know she moved to Auburn. That's great.
And she is still on. So, Nicolette, at least you have one fan. Yeah, that's not giving you a hard time.
Okay. Well, that's my son's at the University of Alabama, so it's a big deal of Bama versus Auburn. But
I haven't heard of that rivalry. Is that a thing?
Okay. Let me ask you. My opinion and campaign in NASA and bear in mind, this is just speculative, so there's no funding or programmatic direction. But I think the next step is to set up a semi-permanent vertiport to vertiport simulator with full-size air taxis and keep it in place for several years so that we could integrate not just weather technologies, air traffic control, and all sorts of things we could do with that. But on the weather front, for example, I'd like to see we bring in a model like FastEddy. We bring in sensing technologies that you've described under WindMap. The Crately's concept. I sorry, the name escapes me, but that sort of thing where you could tie data products to navigation. So I was wondering what your opinion was on that. Do you see any of that happening on the academic or the commercial front you're working with?
Yeah, and so at Mike Monroney, for example, FAA Center in Oklahoma City, they're setting up a vertiport test site. And so we've had those discussions with them, about how we integrate the data from the weather observations into products that they can actually use as part of their kind of research and development component. One of the things that they're really interested in are the terminal procedures and how that impacts what that approach path is going to look like for some of these systems, particularly from an energy conservation standpoint, because certainly they're not going to have the reserves that traditional hydrocarbon based aircraft are going to have. So how does that weather information tie into what that approach path looks like, so they can think about it really from a minimum energy concept? And James, I don't know if you want to add anything on that from your standpoint, and how some of those things might be integrated into a vertiport test capability.
Yeah, I mean, it'd be interesting to do some simulation. So I don't know how close that vertiport is to the downtown area, but if it is, then you're going to have a lot of effects of the buildings depending on what the airflow is. And so, one of the things we've done in the past is doing some like climatological analyses to see, like, given a certain wind direction, what is your preferred route plan, for example, and we could certainly look at efficiencies in that way too, so that you could take advantage of the low level wind field, and both in terms of how it varies by time of day. So like if there's a diurnal pattern that's pretty consistent, you want to take advantage of that. You probably want to avoid areas that have turbulence, because you're going to drain your batteries faster flying through those areas than more smooth flight areas. So yeah, we definitely see a lot of potential there. Ultimately, what we'd like to have is, as we talk about, picking locations where some critical observations can be made routinely to help improve the guidance products, I think. And that's another thing we could use kind of FastEddy as a digital twin of the atmosphere to see, hey, if we make an observation here, most of the time it's pretty representative of a larger area. Whereas if we make one over here where there's a building or something, it's going to be pretty local scale measurement, not really that representative. So those are some of the initial thoughts I have on that.
Okay. What was that name of the FAA contact, Jamie?
It's the Mike Monroney Aeronautical Center. Okay. And we work directly with the director there, Michelle Coppage. But I'm happy to provide a contact with the group that's running the vertiport.
Yeah, that would be interesting.
Yeah.
Okay.
Yeah, and so they're they just started construction on that. They're essentially taking an old radar tower site and taking that base or platform of the radar, turning that into the vertiport landing capability, and essentially building a ground control and hangar below that to be able to take the vehicles. But it's about, I'm guessing, I should know this since I grew up there, but it's probably about 5 miles or so from the downtown area. So there'll be an impact. It does have the tallest tower within the state, the tallest skyscraper within that downtown area. So it would be interesting, and that's we'd actually kind of went back and forth in terms of what made more sense from a study location. NCAR has done a number of studies in the past on Oklahoma City area for for other experiments.
Okay. Yeah, thanks for that, Jamie. Let me ask you all about vehicle sizes. So the vehicles used in WinMap and the stuff I've been doing with NASA up to this point are all small UAS. So as we look to what NASA really wants to do is the full-size air taxis. So the findings under WinMap of sensing capabilities, how would they extend to a full-size air taxi, like a passenger size aircraft? I don't know. Maybe start with Craig. What does Craig think? If Craig's still with us.
No, it looks like Craig is no longer with us.
Oh, okay.
I don't see him on. I know a couple people had to drop off up at the 1 p.m. side. So yeah, I'll jump in, but please feel free, anyone else that wants to kind of add something in there as well. One of the things that we've been developing is essentially a set of capabilities that would allow us to assess the risk based upon the atmospheric environment. So in particular, you can think of winds predominantly is going to be the biggest thing we have to be concerned about in an urban environment. And based upon different criteria, and for winds, we call these a general directional flow, what your background flow is, what the shear is, and then what the level of turbulence is, or general gradient and gust. But that also is dependent upon the size and capability of the vehicle. So that ties into your risk assessment. So there's both an environmental aspect and then a vehicle capability aspect as part of that. And that's going to be both what kind of vehicle it is, fixed wing, rotary wing, and then the capability of those vehicles in different environments. So that's one component of that. And we have some larger vehicles. These are 200, 300, 400, up to 1,500 pound autonomous systems that we're currently testing. They're certainly not ready for this type of evaluation yet and this type of experiment, but they will be in the coming years to help us evaluate that. And so as we're doing that, kind of the next stage of this is to do a twofold approach where we're assessing the capabilities of the vehicles so we have a really good understanding of what those vehicles can endure in various wind environments, and then tie that back into some of those simulations, and then pull that risk matrix out of that. I think Gus, you want to say something?
Yeah, just also a compliment here that a lot of the methods and techniques that we developed for the small scale in terms of integrating the sensor itself to the aircraft will also apply to the larger vehicles, particularly in the methods of characterization of the measurement, because you want to have something equivalent to what's today's MDAR system on manned aviation. And so as the commercial vehicles start flying, they generate their own data back for unmanned traffic management. But we need to know for sure that the measurements that are coming out of them are reliable and trustworthy. So a lot of the methods for integration that were developed for integration and validation developed for the smaller scales, we believe are applicable.
So this is Imran Farouk. I'll jump in because we've worked collaboratively with Craig on some of the wind inference algorithms. We do see that more or less the methods, in addition to just the sensor integration, the methods do project and the methods do scale. Often there are different numbers, right? We've also found, and we have a separate scaling project where we've found that some of the physical characteristics will change. You may have changes in stability and those things just with scale. And so pinning those down for specific vehicle classes is still something that needs some work. But for a large measure, once you've verified that those don't change, the numbers change as far as the specific risk contours, and they need to be specialized to the particular platform. But the basic underlying engineering method does not. You can basically take the same method, put in different numbers, You have to verify some conditions are met such that the scaling does apply. And then you can largely reuse a lot of that same algorithm.
All right, thanks. Good insights there. Let me ask about the culminating flight test there at Tulsa. It was, I think, especially impressive because it was done in an urban or near urban environment. And what kind of feedback or lessons learned did you find, and how do you get all that buy-in from the city? And I mean, did the FAA have to get involved, or were the heights associated with?
Yeah, and that was, there were a lot of challenges here, and I'd like to hear, in particular, James and Gus comment on this, because, they're really the team that were putting together this flight experiment. But on our side, it was getting all the approvals from the FAA. So basically coordinating with James, looking at the map and saying, oh, these are interesting sites, us being able to get first permission from the landowners that, yes, we could operate from there. Some of these were public sites, some were private sites. So we worked with the city, very closely, got their buy-in, but then of course, working through the FAA to be able to get flight approvals. I don't think I included, I should have put the airspace map on here, but a lot of these were directly within the shelf of the Tulsa Class C airspace, and so the FAA was surprisingly obliging, to let us operate within these particular areas. So in addition to Tulsa International Airport, which sits about here, we also have the busiest airport in the state, which is used as a flight training facility down here. And so there were, a lot of cases where we had active air traffic in the area as we were operating these systems. And I think it does show a good case study of the art of the possible.
Yeah, it's for sure something I wanted to highlight as one of the firsts as well. My team in particular, we were a couple of days located inside the property of a local airport, and so we're flying within very few feet from the runway of an airport in Skiatook, which was really interesting experience, not only because you had to pay attention to everything that was around you, but also in terms of coordination with other teams and all of that. And I believe this creates a twofold lesson. One for future studies in weather UAS, so that we can do these operations. And correct me if I'm wrong, Jamie, but I believe in several of the outer ring sites we actually had permission to go to 5,000 feet. And within the inner rings, we're going to 2,000 feet AGL, if I'm not mistaken.
Yes. Yeah, and they were higher in some cases. So
yes, and so the coordination definitely sets a precedent for weather UAS research, because to your earlier question of scaling, I think there's a point where these tools have to be implemented in conjunction with the larger scale, right? They have to be maybe paired with a vertiport, so you can have better profiles near your landing facility, right? Because as my understanding of AAM, one of the biggest concerns is not only the trajectory, but the lack of weather information upon arrival, right? And so this twofold effect of enabling future research of weather UAS and how this tool enters operational workflows, but also how can you coordinate to such a scale with authorities and do it safely, because we had no incidents and we were doing 8 to 10 flights per site per day, 4 days. And Jamie, sorry, not Jamie, James, if you want to jump in and give us a ballpark of total count of profiles that were generated, but just great to give you an idea, it was 8, 10 per site during 4 days?
We currently have about 900 profiles that were uploaded to the Amazon Web Service WMO demonstration campaign bucket. So 900 flights in about 5 days, which is pretty substantial. I was also going to note that some of the operators had some issues in the downtown area with interference with Wi-Fi. They were picking up signals from like 50 different Wi-Fi platforms like in the area. And so they actually had to move to another location because there was so much interference with their system. So that's one thing that we need to, I think, be aware of, that there could be Wi-Fi issues. And then also the GPS denied areas of the urban landscape. A couple of our operators, at least that I'm aware of, had issues with GPS dropping out, which was interesting. I don't know how widespread that was, though. That'd be good to know ultimately for the experiment.
Okay, yeah, thanks for the discussion. Yeah, that was it's an impressive culmination, not just because of the urban environment, but I think it's unprecedented, and in that it was an end-to-end. You know, it assimilated the data, put it into models, so it was, I think, unique and an innovation in that regard of,
Yeah, for sure.
of getting everything integrated together. So.
But
Yeah, very nice.
I know James will still be working on this for a bit.
Yeah, I mean, all the infrastructure is in place. It's just a matter of doing the simulations now and assessing what the actual impact was of the observations. Unfortunately, the weather wasn't super interesting most of the days, but there were definitely subtle wind shifts that happened throughout the campaign. And so those are of for sure interest in UAM and AAM operations that we'll be looking at more closely.
Yeah, excellent. It's getting late and I've been talking a lot, so maybe I'll be quiet and see if anybody else wants to bring anything up.
Hey, Jamie, this is Kaushik, if you don't mind. A couple of things that you mentioned before, even if you don't answer it now, if you put it in your final report, that'll be great. You talked about follow-on work with NOAA, and I'm sure your team is, other sets of teams are working with other work so that this work continues on in the future. If you can capture that, that's also very useful information for us.
Yeah, and we'll do that across the board because I know it's not just us, but other folks on this call, as part of the team are moving to follow-up projects as well. While we don't have a global one, in the past we've been pursuing a National Science Foundation Engineering Research Center really focused around this. It's not I would say a great fit for what NSF typically does, but we're still focused on trying to make that happen at some point in the future because we think it's an important enough problem, for NSF to be able to support. But certainly between NOAA and the National Weather Service, as well as NIST, we have ongoing projects that are following up on this and using this as really the foundation for that. Because there's still a lot of work to be done, particularly if you think about this, integrating this into a true 3D MESNET capability. There's a whole wide range of questions there that just have not been answered.
Yeah, so apart from the government, are there any private companies that are willing to pay for this going from the next level of TRL? Or
if they can figure out, how they monetize it, right? And I think this is a good example. The picture that we have up here is a Meteo drone, and so that's from a company called Meteomatics, and they have, we'll call it a full commercial solution with a drone in the box that provides autonomous capabilities. You don't have to be there. You can push the button remotely. You'll watch it from your camera, have the system take off, profile up to 20,000 feet. And then you come back down and land. Now integrating that both in terms of the data out to the end user for integration, as well as just integration into the NAS and making that system work, has a lot of hurdles before that can happen. So one of the things that we're doing in particular right now is evaluating some of the commercial systems. How well do they do data compared, from one to another, for example. This system works really well at, distances, not very close to the ground, right? You really have to be a couple hundred feet AGL before you start to get good data off of it. What kind of impact does that have? If you're missing that, first 200 or 300 feet, that you're able to get. There are a lot of potential for that. And, Gus had showed in his intercomparison campaign, both of those systems there are systems that are under commercialization right now by different companies.
Yeah, I have a quick question for James. So you were talking about FastSD as being the primary one that you're going to keep pursuing. Is that what if it goes out to the industrial partners like Aviation, are they also pursuing the same methodologies as you are?
Yeah, I mean, the big thing about FastEddy is it's a GPU system. So that's why it's called FastEddy, is it runs 7 or 8 times faster than like a CPU-based LES system. And what that allows us to do is actually resolve building structures. And we've gone down to 2-meter resolution. The simulations I was showing are 5-meter, but without that capability, it would take so long to run that you wouldn't be able to do many simulations in real time. So the nice thing about FastEddy is we can actually do, especially if it was a little bit coarser, pretty large areas in real time and provide that information to users. And we do provide it's open source code that's available on Git. Of course, we have our own research version that's more advanced typically. But we make new releases once per year. So if commercial vendors want to work with us, we could definitely help them set the system up and run it as well.
I'm happy to answer from the Climavision side of things too. I mean, like James said, yeah, I mean, there's a lot of capabilities here on the private sector side as well. Like the example that I gave of the high resolution model that we're running right now. Now, obviously, we don't do the level of, detailed modeling like the work that NCAR has done in this sort of, research to operational capacity. And the challenges, I mean, primarily are around, the processing power that's required for all of that and the related costs. So it comes down, I think, primarily to the business case for us to do that. There are other situations where like a high resolution model is helpful for energy, for example, and those types of, applications we keep developing on the private sector side. But when it comes to like urban modeling, computational fluid dynamics, the use cases over there are fairly narrow, maybe restricted more to like, EPA type applications right now commercially. So we're really waiting and observing how the industry scales on a UAS and AM side to step up like the commercialization and development of, those types of models, if that's helpful.
Yeah, if I may chime in here, kind of tying the last 2 questions together. As mentioned, we had an effort in 2018 lapse rate that was actually part of a previous NASA activity. And one of the interesting differences between 2018 and 2014 is that in the intercomparison study was that one of the systems from 2018 that became patented and then was licensed to a company became already a product in this market, and several teams in 2024 actually had purchased that system and were using it. I believe 3 or 4 NOAA teams had purchased that system and were using it as their system for participating in the field campaign. And as an extension of that effort, Dr. Avery and I at Oklahoma State University have a partnership with the Tulsa National Weather Service office that created a good momentum to help us get the permissions that we needed, along with other things, obviously, because we're working with them on using already the format that comes from the WMO demonstration that was used in the campaign to stream our data to them, and setting up even a online service for whenever we fly, they get the data automatically. And so we're studying how that gels into their workflow and how they can leverage it. And we're also studying what are the situations where you could do an automated commercial system, and what are the situations where you need a more research grade, bespoke, let's say, profile done for the measurement for the forecast to yield better results.
Thanks. So Gus, you're essentially saying that the systems that you're setting up will become the de facto standards in a way. Is that what you're hinting at?
Partially, yes. Partially because of convenience, right? Not all weather interested parties have the engineering capability or interests of developing these technologies. So when these technologies do become patented and are well known and trusted, it is easier and more convenient for them to just purchase once a company such as Intermet Systems licenses the technology and makes a product out of it. But certainly the methods that were behind the design are becoming the standards for other developers, which is interesting you bring that word up, standard, because both Jamie and I participate in an STM effort that is looking at the means of compliance for third-party weather providers for the FAA to generate information in support of the introduction of AAM, right? And so Jamie and I are leading the standardization of these measurements and how companies will need to demonstrate compliance to these standards to be used by government agencies as third-party providers, without the overhead of these agencies having to certify them one by one. And so, yes, there is an ecosystem that is being born out of these efforts that honestly are only possible because of the magnitude of this ULI. The amount of work that was done under this ULI, it would be very hard to emulate with smaller individual projects.
I'm glad I asked these questions. Thank you very much, all of you, for your answers.
Yeah, and I'd like to, thank Grady, Mina, Koshik. This has been a fantastic program for us. I think it's been transformational for all of our teams. We know that it's garnered a lot of interest in various communities. It's an intersection between aviation, the traditional kind of aviation weather, and of course the new fields coming on related to autonomous weather observations. And I do think its impact will live on for quite some time. So we appreciate all the efforts, from the NASA team in running the program and making this all possible.
Hey, apart from thanking all the investigators, I want to thank you too, Jamie, for leading such a good team.
It's been an honor. It's been such a great group of folks. So yeah, I wish we could go on for another 4 or 5 years. So
that's a
Yeah, it's been fun working with everyone, and I'm sure we'll find other ways to collaborate in the future.
That's the nice thing about these ULIs. You make connections, and hopefully you'll have some great relationships in the future. Jamie, if you could please provide the charts to Grady or myself, and we'll make sure to share them amongst at NASA.
I'll provide that as well as the recording.
Perfect. Thank you.
All right. Thank you all. And I think with that, we will bid adieu.
All right. Fantastic.
Thanks, everyone.
Great job, everyone.
Bye. Thank you.
Thanks.
Say hi to Taylor for me, Grady. Of course, you don't hear much anymore, do you? Since you moved.
No, well, I saw her. We were 2 weeks out at Edwards Air Force Base.
Oh, okay.
Last week, looking at the Joby S4. That was very cool.
Oh, very nice. I'm jealous.
Yep. And she's applied to graduate school.
Good. Well,
Virginia Tech.
Fantastic. Well, we know some good people there. So
a few, yeah.
Thank you much.
Yep. See ya.
Take care.